Hello there and welcome to Physics with William, where curiosity gets cosy and science takes the scenic route to slumber. Tonight, we are settling in beside one of the strangest boundaries in all of physics, a place so small that even the word small begins to lose its ordinary meaning. We are going to ask a question that sounds simple at first, and then becomes wonderfully difficult the longer you sit with it. Why can we not measure anything below the Planck scale? That may sound like the sort of question invented by an overly ambitious microscope, or perhaps by a ruler that refused to accept its own limitations, and yet it is one of the most serious questions modern physics can ask. Because measuring things is one of the main ways we make sense of the world. We measure time, distance, temperature, weight, speed, pressure, brightness, and all the other things that help us turn the universe from a blur into something a little more manageable. We place marks on clocks, numbers on screens, lines on maps, and labels on jars. Measuring is how we take the wildness of reality and persuade it, just for a moment, to sit still. But there comes a point, somewhere unimaginably far beneath atoms and particles and anything your senses would ever notice, where that whole project begins to wobble. Not because our tools are clumsy, though they certainly can be. Not because we have not yet built a machine clever enough, though physicists would very much enjoy doing exactly that. No, the difficulty seems to run deeper. It may be that below a certain scale, nature itself stops allowing measurement in the ordinary way. Not simply because the task is hard, but because the very ideas of distance and position and size begin to behave less like firm instructions and more like rough suggestions. Before we get there, though, I would love to know where in the world you are listening from tonight, and what time it is in your little corner of things right now. There is something fitting about that, I think. A discussion about the smallest possible scale, and yet here we are, spread out across cities and towns and time zones, each listening from a different patch of Earth, each keeping our own quiet hour. And if you find this soothing, interesting, or simply a pleasant way to let your mind drift somewhere unusual before sleep, I would be very grateful if you gave the video a like, maybe subscribed, and joined me again for another gentle wander through the stranger corners of physics. It helps this calm little space find its way to more curious minds, and I am always glad to have the company. Now then, let us ease into the matter properly, because this question does not really begin with the Planck scale. It begins with something much more familiar. It begins with the very ordinary act of trying to find out where something is. Imagine for a moment that you place a tiny grain of dust on a table and decide you want to know its exact position. That seems reasonable enough. You look at it. There it is. A tiny speck sitting in one spot rather than another. If you want to be more precise, you use a magnifying glass. More precise still, a microscope. Better instruments let you narrow things down. They let you say not merely that the dust is on the table, but that it is near the edge, beside a faint scratch in the wood, perhaps just to the left of a crumb that really ought to have been cleaned up earlier. So far, so sensible. This is how measurement usually feels. Cruder tools give broad answers, finer tools give sharper ones. We assume that if we just keep improving our equipment, sharpening our lenses, reducing noise and eliminating error, we can continue this process forever. We can always zoom in further, always refine the answer, always replace an approximate position with a more exact one. It is a very comforting idea, rather like believing there is always a smaller box inside the box you have just opened. And in daily life, it works beautifully. If you want to know the width of a table, a tape measure will do. If you want the width of a human hair, you may need a microscope. If you want the size of an atom, things get much trickier, but physics has developed clever ways to approach it. For a long time, the history of science looked like a steady victory march of improved measurement. Better clocks, better telescopes, better scales, better detectors, better patience, which is often the least celebrated but perhaps most necessary scientific instrument of all. Then the universe starts behaving like a host who is happy to show you the sitting room, the dining room and perhaps the garden, but becomes noticeably less cooperative when you start opening doors marked private. At very small scales, measuring something is not as simple as passively observing it. You cannot just peer more carefully and leave the thing untouched. To detect something tiny, you must interact with it. You must prod it in some way. You must use light or particles or some kind of probe, and that is where the trouble begins. If an object is large by human standards, the act of measuring it hardly changes it at all. Shine a flashlight on a football, and the football does not fly off the field in protest. Look at a mountain through binoculars, and the mountain remains impressively indifferent. But when the thing you are trying to inspect is extremely small, the act of inspection becomes part of the story. You do not merely look, you interfere. That alone is already strange enough to unsettle our common sense, but physics does not stop there. Because the smaller the thing you are trying to measure, the more delicate the situation becomes. And the more precisely you want to pin down a location, the more energetic your probe generally needs to be. To see finer detail, you need shorter wavelengths, sharper probes, more concentrated attention from nature itself. Looking more closely is not free, it has a cost. This is one of the first big turns in the road, and it helps to pause here because it marks a genuine shift in how the universe behaves. In ordinary life, better measurement usually just means better craftsmanship, a more careful watchmaker, a better ruler, a steadier hand. In the deep microscopic world, better measurement means stronger disturbance. The more you insist on precision, the more violently you may have to interact with the thing you are trying to understand. That would already be inconvenient if it were merely a practical engineering issue. But the deeper message of modern physics is that this disturbance is not just a flaw in our current devices, it seems built into the structure of reality. The world at very small scales does not sit still and wait to be neatly described. It resists being cornered in the way familiar objects do, and that resistance becomes sharper and stranger as we move downward through scale. At first, matter looks solid. Then you discover atoms and realize that solid things are mostly empty space with organized structure. Then you look deeper and find smaller constituents, then deeper still, and the picture becomes less like tiny billiard balls and more like something abstract, restless, and probabilistic. The universe stops resembling miniature furniture and starts resembling a set of rules that only occasionally tolerate simple pictures. By the time you're discussing the Planck scale, you're not merely asking whether your microscope is good enough. You're asking whether the concepts behind the microscope still make sense. Does it still mean anything to ask for a distance smaller than that scale, in the same straightforward way you ask for the width of a hair or the size of a grain of salt? Is space still smooth down there? Can points be defined indefinitely? Can location be specified without limit? Or are we pressing language and measurement tools into a region where they no longer have the right to feel so confident? This is where the topic becomes genuinely profound, though not in a vague or mystical way. It is not profound because it sounds mysterious in the dark. It is profound because the best theories we have, the ones that describe the large universe and the tiny one, begin to pull against each other at this depth. On one side, we have the physics of the very small quantum mechanics, which tells us that uncertainty is not just ignorance, and that particles do not behave like neat little pebbles with fixed properties waiting to be read off a list. On the other side, we have gravity, described by general relativity, which tells us that space and time are not rigid containers but active parts of the physical world. Usually these two great theories are each brilliant in their own territory. Quantum mechanics handles the tiny with astonishing accuracy. Relativity handles gravity and the large-scale structure of the universe with extraordinary success. But push toward the Planck scale and both seem to demand attention at once. The tiny becomes so tiny and the energies involved so severe that you can no longer ignore gravity while talking about quantum behavior. This is rather inconvenient, because the two theories do not combine neatly. They are both magnificent, they are both experimentally successful, and together, at this extreme scale, they start behaving like two highly intelligent guests at dinner who refuse to agree on how the table ought to be arranged. That clash is one reason the Planck scale matters so much. It is not just a small number, it is the scale where our current understanding of reality may cease to be coherent in the usual way. And once that happens, measurement itself becomes questionable, because measurement depends on having a stable framework in which distances, durations, and positions can be meaningfully defined. To put it another way, measuring something requires more than an instrument. It requires a world that cooperates with the idea of measurement. It requires that space be smooth enough, time be steady enough, and interactions be tame enough for the question, where is it, to have a sensible answer. If the fabric of reality becomes too unstable, too fluctuating, too tangled with quantum uncertainty and gravitational effects, then asking for an exact distance below a certain scale may be like asking for the exact shape of a wave while you're inside a storm and the water itself will not hold still. Now, when people first hear that, there is often a temptation to imagine that the Planck scale is just very, very small, in the ordinary sense, like the universe has a final tiny brick, and below that there is simply nothing. But that picture may be too simple. Physics has not proven that reality is built from literal little cubes or fixed bits of length, the way a digital image is made of square pixels. The Planck scale is more subtle than that. It is a boundary where our current methods of description may break down, a warning sign, not necessarily a brick wall with a neat label on it. And that distinction matters because it stops us from thinking of the Planck scale as merely another object waiting to be discovered, like a smaller atom or a tinier particle hiding beneath the others. It may instead represent a limit in principle, not the next thing down, but the point beyond which our usual questions are no longer well formed. That is a peculiar possibility to sit with, because it means the universe may contain not just things we have not yet measured, but regions of inquiry where measurement in the usual sense is not available at all. Science is very good at living with difficult questions. Scientists can tolerate uncertainty, missing data, odd results, and decades of slow progress. But the idea that a question might fail, not because we are lazy or underfunded, but because nature itself refuses to cash the check our language has written, that is a different kind of challenge. Still, it would be wrong to think of this as defeat. Physics has always advanced by discovering not only new answers, but also the hidden assumptions inside old questions. Sometimes the real progress comes not from measuring a thing directly, but from realizing why the original request was framed in a way the universe does not honor. Take motion, for example. It once seemed obvious that time and space were fixed backgrounds and that motion happened within them. Then relativity showed that the background was not so fixed after all. Or take particles. It once seemed obvious they should have clean trajectories and definite properties at all times. Then quantum theory informed us with some firmness that the microscopic world had other plans. In each case, science did not simply hit a wall and stop. It learned that the wall was partly made of its own assumptions. So when we ask why we cannot measure anything below the Planck scale, we're also asking whether our idea of measurement is tied to a picture of reality that only works above a certain level. We may be like sailors whose maps are excellent near the coast, but whose methods become unreliable in waters where the sea itself changes character. That, I think, is one of the reasons this topic feels so compelling. It is not just a story about tiny distances. It is a story about the limits of access, about how far observation can go before observation changes what it seeks, about whether the universe is smooth all the way down, or whether smoothness is merely a luxury of larger scales, about whether space is something that exists fundamentally, or whether it may itself emerge from deeper ingredients that do not look spatial at all. And if that sounds unsettling, there is something oddly reassuring about it as well, because it reminds us that science is not a collection of smug final answers. It is an ongoing negotiation with reality. We ask what can be known. Reality responds, sometimes kindly, sometimes with baffling silence, and occasionally with a result so strange that entire careers are spent figuring out what on earth, or off it, meant. The The Planck scale sits inside that kind of silence. Not empty silence, but active silence. A place where our best tools speak more softly, where theories begin to overlap uncomfortably, and where the simple confidence of ruler and clock gives way to something more careful. It is as if the universe allows us closer and closer through atoms and nuclei and quantum fields, and then says, quite politely but with unmistakable firmness, this is where your usual habits of thought begin to fail. Of course, physicists being physicists, that does not stop them. Quite the opposite, really. Tell a physicist that a region of nature may not permit ordinary description, and you have effectively ensured that generations of them will devote their lives to finding a better description. There is probably no stronger fuel in science than being told the current map is incomplete. That is how whole new theories are born, not from comfort, but from friction. So as we settle into this question, it helps not to treat the Planck scale as some forbidding final door with a keep-out sign hanging on it. It is more like the edge of our present vocabulary, a place where the old words, distance, position, measurement, even space-time itself, may need to be translated into something deeper before the conversation can continue. And that is where we are headed next. Because before we can understand why nothing below that scale can be measured in the ordinary way, we need to get clearer about what the Planck scale actually is, how small it really is, and why physicists treat it not as a random curiosity, but as a turning point where the structure of reality may stop behaving like the world our intuitions were built for. To get a feel for why the Planck scale matters, it helps to slow down and ask a simpler question first. What do we really mean when we say something is small? In ordinary life, small is a button fallen under the sofa, a grain of sugar on the counter, a screw dropped on the floor and instantly swallowed by the carpet as if the house itself has taken a personal interest in mechanical inconvenience. Small is relative. A pebble is small next to a hill. A cat is small next to an elephant. A fingernail clipping is small next to just about everything, and still manages to appear in places you do not remember putting it. Our sense of size is built from comparison, from bodies and rooms and household objects, from the scale of daily life. Physics, however, quickly teaches us that the universe is not obliged to stay on the scale of daily life. Once you begin asking how matter is built and how deep measurement can go, your ordinary sense of smallness starts to break apart. There is small in the familiar sense, and then there is small in the atomic sense, and then there is small in the subatomic sense, and then there is a kind of smallness so extreme that language begins to feel like it is arriving late and without the right paperwork. Start with something easy enough to picture. A human hair is thin. If you hold one between your fingers, it already feels delicate, almost barely there. The sort of thing that can vanish against a shirt or drift onto a page unnoticed. Yet human hair is enormous compared with the structures physics deals with every day. A red blood cell is much smaller. A bacterium is smaller still. A virus is smaller than that. Already, before we have even reached the atom, we're in a world where normal vision gives up and magnification has to do the work. Then comes the atom, which for a long time people treated as the smallest unit of matter, the final indivisible little bead at the bottom of the hierarchy. That turned out not to be the end of the story at all. Atoms have structure. They are mostly empty space, with a tiny dense nucleus at the centre, and electrons arranged in ways that do not resemble little planets, nearly as neatly as classroom posters once implied. Go inward again, and the nucleus itself is made of protons and neutrons. Go inward again, and those are built from still smaller ingredients. What once looked like the bottom layer keeps revealing trapdoors. This history matters because it trains our intuition in a very particular way. We begin to assume that smallness is simply a staircase with no bottom, that every time science reaches a new scale, it will eventually uncover a smaller one beneath it. After all, that is more or less what happened for centuries. First molecules, then atoms, then nuclei, then smaller constituents still. So it is natural to imagine that the Planck scale is just one more rung. Very tiny, yes. Very difficult, certainly. Very difficult. But still just another level waiting for a sufficiently clever machine. That is where the Planck scale differs from the familiar story. It is not merely smaller than atoms or smaller than particles in the usual sense. It is so far below those scales that even saying farther below does not quite capture it. The gap between ordinary human size and atomic size is already staggering. The gap between atomic physics and the Planck scale is more severe still. If you tried to compare them using the language of everyday shrinking, it would feel almost misleading, because nothing in daily experience gives a proper sense of the distance involved. One reason for this is that our minds are not designed to feel exponential differences with much grace. Tell someone that one object is twice as large as another, and they can picture it. Tell them it is 1,000 times larger, and they can still nod along more or less. Tell them the relevant scales differ by unimaginably many orders of magnitude, and the imagination begins to tire. It does not rebel exactly. It simply sits down and asks whether a cup of tea might be more manageable. So let us approach it another way. Think of all the invisible structure beneath the surface of matter that science has already uncovered. Think of how astonishing it was to discover that solid objects are built from atoms. Then think of how surprising it was to discover that atoms are not final. Now imagine a scale so far beneath even those subatomic layers that the ordinary idea of distance itself may not continue to behave properly. That is the territory the Planck scale gestures toward. Not just the very small, but the very small at the point where our usual physical descriptions begin to lose their footing. The Planck scale gets its importance from something quite specific. It is not an arbitrary line drawn by physicists because they enjoy making difficult charts and intimidating undergraduates. It emerges when you combine some of the deepest ingredients in modern physics. On the one hand, there is quantum theory, which governs the small and tells us that nature is not perfectly smooth and predictable in the way older physics once hoped. On the other hand, there is relativity, which teaches that space and time are part of the physical structure of the world, and that gravity is not just a force acting inside a stage, but something bound up with the stage itself. Then there is the scale set by the strength of gravity, and the speed with which signals and influences can travel. When these basic ingredients are brought together, they naturally define a realm where both quantum effects and gravitational effects become equally impossible to ignore. That meeting point is what gives the Planck scale its status. It is the place where the very small is no longer just the business of quantum theory, and gravity is no longer something that can be safely left to the side. Above that scale, in most laboratory situations, gravity is so weak compared with the other interactions that particle physicists can mostly set it aside. At large scales, quantum fuzziness often becomes irrelevant enough that relativity can treat spacetime as a smooth structure. But at the Planck scale, the two major ways of understanding reality collide in earnest. The tiny becomes so extreme that the structure of spacetime itself may start to fluctuate. And once spacetime fluctuates, you no longer have a calm measuring board on which to place your marks. That is why physicists speak of the Planck length with such care. It is not merely the shortest thing we happen to have encountered so far. It is the length scale at which our best theories strongly suggest that the smooth geometry of space may stop being a reliable assumption. Below that, it may not make sense to imagine distance in the same clean way at all. This is where it helps to clear up a common misunderstanding. The Planck length is sometimes casually described as the smallest possible length. That phrase is useful as a rough guide, but it can also mislead. It tempts people to imagine the universe as if it were made of little fixed bricks, each one exactly that size, like bathroom tiles laid down by a cosmic contractor with a very steady hand. Physics does not actually know that spacetime is built in that literal way. Some theories hint at discreteness, others suggest something more subtle. The safer point is this. Once you reach that scale, our current methods for defining and measuring length may cease to work in the way we expect. That distinction may sound modest, but it is crucial. If you say the Planck length is definitely the smallest possible chunk of space, you are making a strong claim about what reality is made of. If you say instead that the Planck scale marks the place where the notion of ordinary measurable length becomes unstable, you are making a more careful claim. You're saying that our map becomes unreliable there, not necessarily that we have already seen the final train. In that sense, meeting the Planck scale is less like finding a tiny pebble at the bottom of the ocean, and more like reaching a region where the water, the light, and even the idea of up and down all start misbehaving at once. The problem is not just that things are hidden. The problem is that the rules we rely on to describe location and size may themselves be part of what is changing. Another reason this scale is difficult to picture is that human intuition quietly assumes continuity. We think of space as something that can always be divided further. Take a meter and cut it in half, then cut the half in half, then again. There seems no reason in ordinary geometry why the process should stop. Pure mathematics can happily continue this game forever. Physics is not obliged to follow that exact script. Mathematics can define endlessly smaller intervals without ever asking how nature would allow them to be measured. Physics, by contrast, must eventually ask what operational meaning the division has. What does it take to tell that one interval is smaller than another? What sort of interaction would reveal it? What kind of probe would you need? And what would that probe do to the region you're trying to inspect? This is one of the quiet but profound shifts that happens as we get closer to the Planck scale. Smallness stops being a purely geometric idea and becomes an operational one. It is not enough to say that a smaller interval can be imagined. One has to ask whether such an interval can be physically distinguished, physically accessed, physically measured. A line on paper can be subdivided in thought without limit. Nature may not permit the same freedom in practice. Once you begin thinking this way, the Planck scale stops looking like a mere tiny number and starts looking like a test of what a physical concept must be in order to count as meaningful. Can a length be real in physics if no possible experiment could single it out? Can a point in space be considered definite if any attempt to isolate it would destabilize the space-time around it? These are no longer questions about numerical precision alone. They are questions about what sort of world makes measurement possible. There is also a humbling lesson buried in the scale itself. The universe is not just large beyond ordinary experience. It is small beyond ordinary experience as well. We often marvel at the vastness of galaxies and the depth of cosmic time, and rightly so. But there is an equal form of astonishment in realizing how far downward the ladder seems to go before our best understanding begins to fray. The Planck scale is a reminder that human beings stand in the middle of reality, not near its upper edge or lower edge, but somewhere in between, adapted to the comforting dimensions of apples, doors, clouds, footsteps, and coffee cups. We are creatures of the middle range. Both the cosmic and the ultramicroscopic require theory to extend us beyond ourselves. That extension has been one of the great triumphs of science. No one has ever held the Planck scale in their hand or watched it through a microscope. It is not known because someone happened to squint particularly well one afternoon. It is inferred from the structure of our deepest theories. It arises when the constants that govern quantum behavior, gravity, and relativistic causality are woven together. That is one of the reasons physicists take it seriously. It is not a whimsical proposal. It is a scale written into the architecture of the theories that have already proven themselves over and over in their respective domains. Yet even here, science remains careful. The Planck scale is meaningful, but what exactly happens there is still uncertain. Different approaches to quantum gravity paint different pictures. Some suggest space-time may have a grainy structure. Some suggest that what we call space emerges from more fundamental relations that are not spatial in any simple sense. Some imply that the very distinction between before and after, here and there, may need to be revised. In all of these cases, the Planck scale serves as a kind of threshold, not the place where all answers are finished, but the place where the old questions must be rewritten with great care. This makes it one of the most exciting scales in physics, though perhaps not in the loud, glamorous way excitement is usually advertised. There are no dramatic sparks flying off the side of a telescope, no cheerful laboratory machine producing Planck scale samples in a tray. The excitement is more austere than that. It lies in the realization that this scale may mark the edge of the conceptual framework we currently use to describe reality. Few things are more thrilling to a theoretical physicist than discovering the exact place where a successful theory stops being enough. It means there is genuine new ground to cover, and perhaps there is something quietly beautiful in that. The Planck scale is not simply tiny, it is instructive. It tells us that size is not the only issue. Context matters. A flea is small relative to a dog. An atom is small relative to a grain of dust. The Planck scale is small relative to everything we can currently probe, yes, but its real significance comes from being the scale where smallness itself becomes entangled with the structure of spacetime, the meaning of measurement, and the unfinished business between quantum theory and gravity. So when we ask how small is small, the answer is not just a matter of ever finer comparison, it is a matter of learning that there may be a lower boundary to what size can mean in operational physics. Not because mathematics gives out, and not because imagination becomes illegal, but because the physical world may stop supporting the smooth background that our ordinary idea of size assumes, and that is the key thing to carry forward. The Planck scale is not famous merely for being tiny. It is famous because it stands where our usual picture of a measurable world begins to wobble. Once you see that, the next question comes into view almost immediately. If this scale is where length and distance become difficult to define in the usual way, then what does it actually mean to measure anything at all, and what hidden assumptions are tucked inside that apparently simple act? To understand why anything below the Planck scale becomes so difficult to talk about, it helps to pause over a word that usually seems harmless. Measure. It sounds straightforward, almost domestic. We measure flour into a bowl. We measure a room for a bookshelf. We measure a child against a wall each year to see how much they have grown. We measure time while waiting for water to boil, though that particular measurement has a way of becoming emotionally unreliable after the first minute or so. In ordinary life, measurement feels like one of the simplest things we do. It feels like reading off what is already there. That feeling is useful, but it is also a little deceptive, because the moment physics begins asking what measurement really is, the whole business becomes far stranger than rulers and kitchen scales have led us to believe. Measuring is not just reading a number. It is not a passive act. It is not simply the universe sitting quietly while we write down one of its properties in a notebook. Measurement is an interaction. It is a physical event. It is one part of reality making contact with another and producing a result that can be recorded, compared, and trusted. That last part matters especially. A measurement is not just a sensation. It is not enough for something to seem big or seem bright or seem long. Physics wants a result that can be shared, a result that does not depend too much on one person being in a good mood, or standing at a convenient angle, or squinting heroically. To measure something is to connect it to a standard, a repeatable procedure, and an apparatus that links the thing being tested to a stable outcome. The more reliable the measurement, the more those links hold firm. This sounds technical, but it begins in a very human way. Suppose you want to know how long a table is. You place a ruler against it. Already, even in this simple case, much more is happening than we tend to notice. You're assuming the ruler itself is trustworthy. You're assuming its markings are stable. You're assuming the table and ruler are sitting still long enough for comparison. You're assuming the light in the room lets you see the markings. You're assuming your eye can line them up well enough. And you're assuming that length is the sort of property that makes sense to compare in this direct way. All of that is so familiar that it disappears into the background. But in physics, background assumptions are often where the real drama is hiding. Once the scales become extremely small, every one of those comfortable assumptions starts to need inspection. What counts as a trustworthy ruler then? What counts as a stable object? What counts as sitting still? What even counts as a position or a length if the thing being measured cannot be isolated without disturbing it? This is why the idea of measurement sits right at the heart of science. Science is not only a collection of theories, it is a practice of connecting theories to the world through controlled encounters. We do not merely imagine that a quantity exists. We devise a way for nature to answer a question about it. That answer may come as a needle moving, a detector clicking, a pattern forming on a screen, a clock ticking differently than expected, or a signal arriving later than it should. But in every case, a measurement is an arranged conversation with reality. We ask in a specific way, nature replies in a specific way, and then we have to decide what the reply actually means. Sometimes that meaning is less obvious than it first appears. Take temperature. It feels like a simple property. Something is hot or cold. But physics had to learn that temperature is not a little fluid hiding inside objects, nor a direct substance you can point to. It is a property tied to motion, energy, and statistical behavior at the microscopic level. Or take color. It seems like a property of objects, yet what we call color depends on light, surfaces, perception, and biological machinery in the eye and brain. So even before we reach the quantum world, physics has already learned an important lesson. What seems immediate is often constructed. Measurement tells us something real, but what it tells us may depend on a whole chain of interpretation. Now, in ordinary measurements, the chain is manageable. You weigh an apple. The scale gives a number. The number corresponds to a calibrated standard. If the scale is good and the conditions are sensible, the result is meaningful. But that success relies on the measured object being large enough and stable enough that the act of measuring does not significantly change it. Place an apple on a scale, and the apple does not become a different fruit out of protest. Shine light on a chair, and the chair does not leap across the room. The world of medium-sized objects is forgiving in this way. It lets us imagine that measurement is mostly observation. The microscopic world is far less forgiving. The smaller the object, the harder it is to detect without influencing it. This is not merely because our hands are clumsy or our devices imperfect, though they certainly are. It is because any measurement requires a physical interaction, and at very small scales, that interaction becomes comparable to the thing itself. If you want to locate something tiny, you must in some sense hit it, or at least make it respond to a probe. Light must scatter from it. Another particle must interact with it. Some signal must be exchanged. Without interaction, there is no information, and once there is interaction, there is disturbance. That word disturbance is doing a great deal of work. In everyday life, disturbance sounds like a nuisance, the sort of thing caused by a neighbour learning drums that now nobody requested. In fundamental physics, disturbance is not an inconvenience layered on top of reality. It is part of how reality becomes knowable. To measure is to disturb. The trick in ordinary science is that the disturbance can often be made small enough to ignore. In the quantum world, that is no longer always possible. This is one of the deepest changes that modern physics forced upon our understanding. It revealed that measurement is not performed from nowhere. There is no perfectly detached observer floating outside the universe, gently inspecting it without consequence. Every apparatus is physical. Every detector is physical. Every observer uses matter, energy, timing, and interaction to obtain a result. That means a measurement cannot be cleaner than the physical laws governing the process that makes it possible. The old dream, if one can call it that, was that nature had definite properties laid out neatly in advance, and measurement simply revealed them. Sometimes this picture still works beautifully. If you measure the height of a building, the result was not brought into being by your tape measure in any dramatic sense. But in the quantum domain, things become more subtle. The outcome you record is tied to the way the measurement was set up. What can be known, how sharply it can be known, and what is left indeterminate are built into the structure of the world itself, not merely into our temporary ignorance. That may sound abstract, so it helps to bring it back to the central question. If someone says they want to measure something below the Planck scale, what exactly are they claiming they will do? Will they locate a region smaller than that with a probe? Will they define a distance shorter than that by comparison? Will they mark off an interval in spacetime more precise than that, and assign it operational meaning? In all such cases, the request assumes that measurement continues to function as a clean sharpening of description. It assumes there is always a finer ruler, a more precise probe, a more exact question. Physics begins to suspect that this assumption may fail. But before we get to that extreme limit, there is another important layer to measurement that deserves attention. Measurement is always relative to a framework. To measure speed, you need a frame of reference. To measure duration, you need a clock. To measure position, you need coordinates or landmarks. To measure energy, you need an interaction that registers energetic differences. None of these quantities float freely without context. Even in ordinary life, asking how far something moved only makes sense relative to some agreed background. Did the train move relative to the station? Certainly. Did it move relative to the person seated inside it? Not in the same way. Relativity sharpened this lesson enormously. It showed that space and time are not absolute backdrops in the old simple sense. Different observers can disagree about durations and distances depending on their motion and gravitational situation, and yet all still describe reality consistently. So measurement already depends on a world that provides enough structure for comparisons to make sense. That is a crucial point. A ruler works because space behaves stably enough for lengths to remain meaningful. A clock works because physical processes can mark duration in a repeatable way. If the very background of space and time becomes unstable, fluctuating, or uncertain, the tools that depend on that background begin to lose their grip. It is hard to measure distance if distance itself is not well defined at the scale you are probing. It is hard to measure duration if the underlying geometry that supports clocks is no longer smooth enough for time intervals to be cleanly distinguished. That is one reason the Planck scale is not merely a challenge of engineering. It is not as though physicists are standing around saying, if only someone would invent a slightly better microscope, this whole business would be sorted by Thursday. The difficulty is more foundational. Measurement relies on concepts such as location, interval, and interaction being well behaved. At sufficiently small scales, especially where quantum effects and gravity both demand attention, those concepts may no longer behave in the familiar way. There is also an oddly practical side to all this. A measurement is not just a theoretical definition. It must leave a record. A detector must end in some state. A screen must show a mark. A circuit must register a signal. Something macroscopic enough must happen that the result can, at least in principle, be communicated. This means every measurement bridges scales. Tiny interactions have to produce larger consequences. The world of the very small must eventually hand its answer up to the world of instruments, computers, notebooks, and occasionally sleep-deprived physicists staring at plots that refuse to look sensible until the third cup of coffee. That bridging process is often hidden from view because laboratory practice has become very sophisticated, but it matters enormously. Measuring is not just about the tiny target, it is about the whole chain by which a microscopic event becomes an accessible fact. If that chain breaks, or if the target cannot be probed without wrecking the conditions that make the chain possible, then measurement itself is in trouble. This is where one begins to appreciate just how remarkable successful physics really is. The world does not owe us measurable quantities. It does not owe us stable regularities, repeatable processes, or entities that can be isolated cleanly enough for comparison. And yet across a huge range of scales, it does. Clocks can be synchronized, spectra can be read, distances can be inferred, particles can be tracked statistically, stars can be weighed from afar, entire histories of the universe can be reconstructed from patterns in radiation. Measurement, for all its philosophical strangeness, works astonishingly well. That very success is part of why the Planck scale is so provocative. It stands at a place where the ordinary logic of improvement may run out. Normally, when a measurement is noisy, we reduce noise. When it is coarse, we refine the apparatus. When the target is too small, we increase resolution. But what if increasing resolution requires so much concentrated probing that spacetime itself becomes part of the disturbance? What if the cost of asking a sharper question is that the region you are asking about no longer remains a calm stage on which a sharp answer can appear? Then the problem is no longer one of craftsmanship, it is one of principle, and perhaps the strangest part is that this does not make measurement meaningless. It makes it more serious. It forces us to ask what we really require from a physical concept before calling it measurable. Is it enough to imagine it mathematically? No. Is it enough to name it? Also no. To count as measurable, a quantity must be tied to a possible procedure, even if only in principle. There must be some conceivable arrangement of the world that would allow that quantity to show itself in a result. If no such procedure can exist without destroying the framework that gives the quantity meaning, then the quantity may not be physically measurable in the ordinary sense. This is not a defeat for science. It is one of its strengths. Science is at its best when it refuses to be impressed by words alone. You can propose all sorts of elegant-sounding ideas, but sooner or later physics asks, what would it mean to observe that? What operation distinguishes this claim from that one? What measurement could tell them apart? Those questions are not narrow, they are what keep the subject honest. They stop us from mistaking linguistic confidence for knowledge. So when we ask what it means to measure anything at all, we're really asking how reality permits itself to be interrogated. We're asking what must be true of the world for questions about length, position, time, and energy to have operational meaning. We're asking how much the answer depends on the apparatus, the interaction, the background structure of space-time, and the unavoidable disturbance built into the act of observation. And the closer we move toward the Planck scale, the more those questions stop being philosophical decorations and become the main event. Because once you take measurements seriously, the next difficulty arrives almost on its own. If every act of measuring something small requires a probe, and if sharper probing demands shorter wavelengths and more concentrated energy, then sooner or later, the very tool meant to reveal the object begins to interfere so strongly that it becomes part of the obstacle. Light, which seems like the most helpful ally in observation, starts causing trouble of its own. And that is where the story naturally turns next, toward the uncomfortable moment when seeing more clearly no longer helps, because the light itself has become the problem. For most of our lives, light feels like the most helpful thing in the world. It lets us find our keys, read a page, avoid walking into furniture, and form the rather optimistic belief that if something is there, then with enough brightness and enough patience we ought to be able to see it. That belief runs very deep. It is one of the quiet assumptions we carry around without noticing. More light means more visibility. Better visibility means more knowledge. Shine a lamp on the matter and the mystery retreats. For a very long time that assumption served science beautifully. Telescopes gathered faint light from distant stars and made the heavens more legible. Microscopes bent and focused light to reveal hidden worlds in drops of water and thin slices of tissue. Lenses, mirrors, polished glass, careful alignment and patient observation turned light into one of the great tools of discovery. Entire revolutions in knowledge began with the simple idea that perhaps if we looked more carefully, and perhaps if we improved the optics, the world would reveal finer detail. And for a while, it did. Cells appeared, tiny organisms appeared, structures invisible to the naked eye became vivid and undeniable. The world opened inward as well as outward. Light was not just useful. It felt cooperative, like a reliable guide that, when properly handled, would always lead us toward greater precision. Then physics discovered that light has rules of its own, and those rules do not always cooperate with our desire to see smaller and smaller things. The trouble begins with something very simple. To see an object clearly, the light you use has to be fine enough to resolve the relevant detail. That is the ordinary version of the story. If the features you're trying to observe are smaller than the scale of the light probing them, the image blurs. Not because the object ceases to exist, but because the probe is too crude for the task. It is rather like trying to inspect the shape of a grain of sand while wearing mittens the size of baking trays. Your efforts may be sincere, but the tool is sending mixed messages. This was one of the first clues that light is not an infinitely obedient servant. It comes in forms with different wavelengths, and wavelength matters enormously. Longer wavelengths are good for some purposes and hopeless for others. If you want to look at structures much smaller than those wavelengths, the light will not give you a sharp answer. It cannot. The probe itself is too broad, too spread out, too blunt for the scale of the question being asked. At this point, the solution seems straightforward enough. Use shorter wavelengths. If visible light is too coarse, move to ultraviolet. If that is still too coarse, move to even more energetic forms of light. Science did exactly this. It kept finding ways to use probes of smaller and smaller effective scale. In that sense, the universe behaved much like an encouraging but slightly stern tutor. If you wanted a better answer, you had to ask a sharper question with a sharper tool. But sharper tools in physics are rarely free. When it comes to light, shorter wavelength goes hand in hand with higher energy, and higher energy means the act of looking becomes more violent. This is the point where light stops being a polite observer and starts behaving more like an overenthusiastic inspector kicking the door open to check whether the hinges are secure. At everyday scales, you can ignore this. Shine a lamp on a bookshelf and the bookshelf remains unmoved, both physically and emotionally. But at very small scales, using high-energy light to find out where something is means delivering a significant jolt to the thing you're trying to inspect. That is not a flaw in our laboratory manners. It is built into the nature of the interaction. Light does not merely illuminate in the abstract. It exchanges energy and momentum with matter. To extract information, something has to happen. A photon has to scatter. A target has to respond. A detector has to register the event. Information arrives because an interaction occurred, and that interaction changes the state of what was measured. Once that becomes important, the whole dream of simply seeing what is there begins to wobble, because if the target is tiny enough and the light energetic enough, then the very act of locating the target can knock it around so strongly that the answer you obtain is inseparable from the disturbance you caused. There is something deeply ironic in this. Light, which feels like the symbol of clarity, turns out to be one of the reasons clarity fails at extreme scales. The better you try to localize a tiny object with shorter wavelength light, the more energy you pack into the process, and the more disruptive the encounter becomes. You gain positional sharpness in one sense, but you pay for it by upsetting other aspects of the system. The thing you wanted to inspect quietly is no longer quiet. It has been shoved, jolted, and entangled with the probe that was meant to reveal it. This is one of those moments in physics where the universe seems to smile faintly and say that your instincts from ordinary life were useful up to a point, but they are now being retired from active duty. It also teaches a more general lesson. Measurement does not scale down in a smooth and innocent way. We like to imagine a microscope as merely a more powerful eye, but at very small scales it becomes something else entirely. It becomes an intervention. You're not just magnifying, you are participating in the event. And when the scale becomes extreme enough, the participation is not optional and not negligible. Historically, this change in viewpoint was unsettling, because it forced science to give up a certain kind of comfort. There had long been a hope, sometimes explicit and sometimes merely assumed, that the world was made of definite things with definite properties, and that better observation would simply reveal them more exactly. Light was supposed to help us lift the curtain. But at the quantum level, the curtain is attached to the stage, and pulling on it shakes the whole performance. One can get a feel for this without mathematics by imagining the absurdity of certain extremes. Suppose you had a tiny object whose location you wanted to pin down ever more precisely. You decide to use light of shorter and shorter wavelength. Each improvement seems like progress. Each time the probe gets finer, but each time the energy involved rises. Eventually, the photon you use to find the object carries so much punch that it does not merely reveal where the object is, it batters the object in the process. The more insistently you ask "where are you?", the more violently you ensure that the answer comes at a cost. This is not some minor technical irritation, the sort of thing future engineers will solve with quieter lasers and a better funding application. It is one of the structural facts of the quantum world. Information is physical, probing is physical. There is no way to separate the knowledge gained from the physical means by which it was gained. That is why light becomes a problem. Not because light stops existing, not because it loses its usefulness altogether, but because its usefulness comes with terms and conditions that become impossible to ignore. At moderate scales, those conditions are gentle. At tiny scales, they are severe. There is another layer to this as well, and it makes the situation even more interesting. Light is not just a wave in the old intuitive sense, spreading smoothly and harmlessly everywhere. Quantum theory teaches that it also behaves in discrete packets. That means the interaction between light and matter is not infinitely soft and divisible. You cannot always take the same probing process and simply reduce its impact to almost nothing while preserving the same resolving power. The granularity matters. The exchange happens in physical chunks, and the chunkiness of the interaction becomes part of what limits what can be known in a single measurement. So when people casually say, perhaps we just need a better microscope, physics has to answer that the microscope itself belongs to the same universe as the target. Its operation is governed by the same laws. It is not magic. It cannot evade the energetic price of short wavelengths. It cannot ask a sharper question without paying a sharper cost. This is one reason why high-energy physics looks the way it does. Instead of gentle magnifying lenses, we end up with particle accelerators and collision experiments. To probe the very small, science does not merely zoom. It hurls particles at other particles and studies the debris. That alone tells you something important. At extreme scales, knowledge does not come from sitting quietly in a well-lit room and peering through a more polished piece of glass. It comes from arranging conditions so violent that hidden structure reveals itself in the aftermath. There is a certain brutal elegance to that. If reality at small scales will not sit still to be inspected, then one learns about it through controlled disruption. Yet this strategy has limits too. The more energy you concentrate into a smaller region, the more the probing event ceases to be a clean measurement of a pre-existing background. Eventually, the background itself becomes unstable. And this is where the story begins to lean toward the Planck scale in a very serious way. Before we go that far, it is worth appreciating just how much our everyday common sense resists this lesson. We're used to thinking that looking does not change things much. The moon is not altered because we admire it. A tree does not shift its branches because we stare thoughtfully at it from the garden. Even many scientific instruments preserve this comfortable impression. A thermometer in a room changes the room only slightly. A tape measure on a wall has little effect on the wall. Light in daily life feels gentle, but gentleness is relative to scale. For a microscopic target, a probe that seems modest from our point of view can be consequential, and once we start demanding extreme precision, modesty leaves the room altogether. The universe does not let us have arbitrarily sharp localization with arbitrarily mild disturbance. That bargain is unavailable. It is also important to see that this is not merely a problem of current technology. People often hear about limits in measurement and instinctively file them under not yet good enough, not yet advanced enough, not yet rich enough, not yet enough lasers, enough cooling, enough calibration, enough elaborate machines humming in underground tunnels. Science certainly has many not yet problems, and history is full of cases where apparent impossibilities became routine with better methods. But the issue here is deeper. It is not just that we have not yet found a non-invasive way for light to resolve arbitrarily small regions. It is that the combination of quantum principles and the physical character of light strongly suggests that no such method can exist in the ordinary sense. That is a very different kind of statement. it means the obstacle is not merely our clumsiness. The obstacle is tied to the way information and interaction are woven together. Once you accept that, the role of light changes in a rather dramatic way. It stops being the universal solvent of ignorance and becomes a participant with limits. It can reveal, but not without touching. It can sharpen, but not without disturbing. It can tell you more, but not without altering the circumstances under which more is being told. And if that sounds almost mischievous on nature's part, there is something oddly fair about it too. Why should the world permit us infinite precision at no cost? Why should reality yield exact local detail without requiring a physical process that matters? We only expect that because our middle-sized lives have lulled us into thinking, observation is almost free. At fundamental scales, observation presents the bill. As the story continues, the consequences become even more severe. Because at sufficiently high energies, the problem is not only that light disturbs the target, the problem is that concentrating enough energy into a tiny enough region may begin to affect space-time itself. Then we're no longer merely worried about knocking around a particle. We're worried about the structure of the measuring arena becoming unstable under the stress of the measurement. That is one of the reasons the Planck scale looms so large. It marks the territory where asking for a finer look with a more energetic probe is no longer a straightforward strategy. The very means by which light helps us resolve smaller distances begins to undermine the assumptions that make distance meaningful. In a sense, the flashlight becomes too powerful for the room. It does not just illuminate the furniture, it starts warping the floorboards. Long before reaching that extreme though, light has already taught us the essential lesson. Seeing is not passive. Precision has a price. The probe is part of the phenomenon. And the dream of endlessly improving resolution runs into a built-in tension between knowing where something is and leaving the rest of its state undisturbed. That tension is not an engineering nuisance. It is a clue about the architecture of reality. So when light becomes a problem, it is not because science has failed. It is because science has discovered enough to realize that the path to deeper knowledge is constrained by the very laws it seeks to understand. Light remains one of the most powerful tools we have ever had, but at the smallest scales it also becomes a reminder that clarity can itself be disruptive. The closer we try to look, the more the act of looking enters the story. And once that fact is taken seriously, we are brought naturally to the next piece of the puzzle. Because behind the trouble with high-energy probes lies a broader principle about uncertainty itself, and about why reality refuses to let all of its details be pinned down at once. Now we arrive at one of the most famous and most misunderstood ideas in modern physics, and it enters the story at exactly the point where our old habits of thought begin to lose their balance. Because once light stops behaving like a harmless lantern and starts acting like a disruptive probe, the next question naturally follows. Is this merely an unfortunate feature of the tools we happen to use, or is there something deeper going on in reality itself? This is where the Heisenberg limit enters, and despite the dramatic reputation it has earned, the basic idea is less theatrical than people sometimes imagine. It is not a mystical fog machine switched on by the universe for effect. It is not a polite way of saying physicists have misplaced the answer and are hoping nobody notices. It is a statement that some pairs of properties cannot both be pinned down with unlimited sharpness at the same time. The world at very small scales is not arranged in a way that permits every detail to be fixed all at once in the clean classical manner our intuition expects. That is already a difficult thing to hear, because the ordinary mind likes a well-behaved object. It likes to imagine a tiny thing as though it were a tiny pebble. The pebble has a position, a speed, a direction, and a path, all there at once, whether anyone checks or not. If our measuring tools are poor, then we may fail to know those details. But the details themselves, in that picture, remain perfectly definite. They are tucked away inside the object, waiting patiently for a better microscope, a steadier hand, or an over-caffeinated graduate student with a grant. Quantum physics does not encourage that picture. In fact, it spends a great deal of time quietly dismantling it. The Heisenberg limit is often introduced in connection with position and momentum, though the heart of it is broader than any single pair of quantities. If you try to make the position of a particle more precise, the momentum becomes less sharply defined. If you try to sharpen the momentum, the position grows less exact. This is not simply because measurement tools are awkward. It is because the state of the particle itself does not support unlimited precision in both respects simultaneously. The blur is not merely in our notes. The blur is in how reality presents itself at that scale. That is a hard sentence for the classical mind to accept. We are trained from childhood to believe that uncertainty is mostly a human shortcoming. If we are unsure where the keys are, it is because we forgot. If we are unsure how much the suitcase weighs, it is because we have not put it on a scale. If we are unsure which train will arrive first, it is because we have not checked the schedule, or because the schedule has entered into a personal disagreement with reality. In each case, uncertainty belongs to us. The world itself remains tidy. Quantum theory challenges that instinct. It says there are cases in which uncertainty is not merely a temporary gap in our information, but part of the structure of what can be meaningfully said. One useful way to approach this is to step away from the idea of particles as tiny marbles. The microscopic entities described by quantum mechanics do not behave like little hardened beads moving through space on neat paths. They behave in ways that force us to use wave-like descriptions as well. And waves do not localize in the same way marbles do. A perfectly spread out wave has a very definite wavelength, but it is not localized to one tiny spot. A tightly localized pulse can tell you where something is, more or less, but it contains a mixture of wavelengths rather than one single clean one. This built-in trade-off lies behind the uncertainty. Sharpness in one respect comes with spread in another. That may sound technical, but the essential idea is almost intuitive once you stop trying to force the wrong metaphor on it. If something behaves in part like a localized event and in part like a wave, then demanding that it have the pinpoint certainty of a classical point particle and the neatly defined momentum of a perfect wave at the same moment is asking for two incompatible simplifications at once. Reality refuses to flatter us that much. Now, there is a common misunderstanding worth addressing because it causes endless confusion. People sometimes hear about the Heisenberg limit and conclude that nothing is real at all, or that particles simply do not have properties until someone glances at them, as though the universe spends most of its time hiding behind a sofa until observed. That is not a helpful way to think about it. The quantum world is real enough. It produces reliable patterns, precise predictions, and experimental results of astonishing accuracy. But what is real there is not always packaged in the classical form we instinctively prefer. The problem is not that reality disappears. The problem is that our familiar categories such as exact trajectory and simultaneous exact values for everything do not survive intact. A better way to think about it is this. Quantum mechanics does not tell us that nature has no structure. It tells us that the structure is different from the one our everyday experience led us to expect. There are lawful limits on what can be jointly specified. There are patterns of probability instead of simple certainty. There are measurement outcomes that depend on how the measurement is arranged. All of this is real. It is just not classical. And in a strange way, that makes the Heisenberg limit more impressive, not less. It is not a shrug from physics. It is a precise statement about the architecture of microscopic reality. It tells us that blur is not just the enemy of knowledge. Blur is part of the content of knowledge. That is an important shift, because once blur is built into the world, the dream of unlimited refinement begins to crack. In ordinary life, if a photograph is blurry, you assume a better camera will fix it. If a map is vague, you redraw it with finer detail. If a measurement is noisy, you improve the instrument. That logic works beautifully in many areas of science, and it remains useful in quantum experiments too, up to a point. But the Heisenberg limit says there is a line beyond which sharpening one aspect of the description necessarily softens another. There is no universal camera setting that captures everything at full resolution. This becomes especially relevant once we start imagining ever smaller scales. Suppose you want to know where a particle is with tremendous precision. To do that, you must use a probe that can localize it sharply. As we have already seen, that generally means using shorter wavelengths and higher energies. But then the interaction becomes more disruptive, and the momentum of the particle becomes correspondingly less predictable. You have not failed to measure carefully. You have reached a place where the very form of carefulness changes. This is one reason the Heisenberg limit is not just about laboratory inconvenience. It is a principle that tells you what sort of questions can be jointly answered in the quantum domain. If you insist on asking for a particle to have both a perfectly definite location and a perfectly definite momentum, you're asking nature to conform to a classical script it does not follow. The mismatch is not in the bookkeeping. The mismatch is in the expectation. There is also something quietly humbling about the fact that this principle applies not because the universe is messy in a sloppy human sense, but because it is lawful in a deeper one. The uncertainty is not random confusion sprinkled over reality like dust on a shelf. It comes out of the way quantum states are structured. The mathematics of the theory says so, the experiments confirm it, and every modern technology built on quantum physics depends on taking that structure seriously. Semiconductors, lasers, magnetic resonance imaging, and whole branches of chemistry rely on a quantum world that behaves according to these rules, not despite them. So when people speak of the Heisenberg limit as though it were merely philosophical decoration, it is worth remembering that this so-called blur runs half the modern world with brisk efficiency. But let us stay with the conceptual side for a moment, because it matters for the larger question of the Planck scale. The blur introduced by quantum mechanics tells us that microscopic reality cannot be carved into arbitrarily sharp classical facts all at once. Already that should make us cautious about what it means to measure smaller and smaller regions. A particle cannot simply be assigned an exact point and an exact motion in the old sense. The more tightly one aspect is constrained, the more the other spreads out. That means the very notion of a perfectly localized event is more delicate than everyday intuition admits. And that is before gravity enters the room. At this stage in the story, we're still mostly dealing with quantum uncertainty on its own terms. That alone is enough to force a revision in how we think about measurement. We are not merely confronting an object that is hard to see. We're confronting a world in which the categories of exact place and exact motion are not simultaneously available with unlimited precision. The object is not hidden behind the blur in some classical way. The blur is part of the quantum state itself. This has a further consequence that often gets overlooked. If blur is fundamental, then the idea of tracing an exact trajectory through space-time starts to lose its meaning at small scales. In classical physics, you could imagine a particle having a path, even if no one had yet measured it. In quantum physics, what you can predict and observe are distributions, amplitudes, and outcomes linked to measurements. The neat little path fades. The story becomes less about a tiny object following a single definite route, and more about a structured range of possibilities that only settle into specific outcomes when a measurement takes place. That does not mean anything goes. Quantum theory is not chaos dressed in respectable language. It is one of the most accurate frameworks science has ever produced. But it is accurate about a world that does not grant the specific kind of certainty classical intuition keeps asking for. And that, I think, is why the Heisenberg limit feels so unsettling even to people who have heard of it for years. It is not just a technical rule. It is a refusal of a certain style of realism, the style that wants every property to sit quietly in place like books on a shelf, all labelled and waiting to be read. Instead, the quantum world offers a more conditional realism. There is structure, but not all classical structure. There are properties, but not always jointly sharp ones. There are outcomes, but they arise through interactions that matter. There is no view from nowhere in which the whole microscopic scene lies still under perfect illumination. By now, you may notice how naturally this connects with the earlier problem of using light as a probe. High-energy light helps localize. Localization sharpens position. But the Heisenberg limit ensures that sharpening position comes with spread elsewhere, and the physical act of probing only intensifies the trouble. So there is a double lesson here. First, the probe disturbs the system. Second, even apart from practical disturbance, the state being probed does not support unlimited simultaneous sharpness in all respects. The limit is not purely in the tool, nor purely in the target, but in the lawful relation between them. That relation is what gives the quantum world its peculiar character. It is not that reality is vague because we are lazy. It is not that reality is fixed in the old classical way, and we keep fumbling the tape measure. It is that at small scales the physical content of a state includes trade-offs that no improvement in apparatus can abolish. You can design experiments to emphasize one property or another. You can be very clever. Physicists are often alarmingly clever when properly motivated, but you cannot outsmart the structure of the theory itself. All of this matters enormously for the question of what lies below the Planck scale, because the temptation is always to say, let us just probe more sharply. Let us squeeze the uncertainty down further. Let us use more energy, more resolution, more concentrated interaction. But the Heisenberg limit warns that sharpening the picture is never a simple act of reduction. There are consequences. Blur migrates. Disturbance increases. The measurement setup becomes more invasive. And once the scales are small enough, the energy involved may begin to affect not only the particle, but the space-time around it. That is why the uncertainty principle is not a side remark in this story. It is one of the main gates through which we must pass. It teaches us that the microscopic world already resists unlimited classical specification long before the Planck scale is reached. Reality is not a perfectly crisp image waiting for a better lens. It is a quantum world with lawful blur built into its description. And if that is true of particles moving in space-time, one begins to wonder what happens when space-time itself is subjected to the same kind of scrutiny. Because that is the real tension waiting ahead. Quantum mechanics tells us that the small comes with uncertainty. General relativity tells us that gravity is the geometry of space-time itself. Push far enough down in scale, and you no longer get to treat those as separate stories. The blur of quantum theory and the dynamical character of space-time must meet. And when they do, we are brought to the next turn in the road, where quantum mechanics and gravity stop politely taking turns and begin colliding in earnest. Up to this point we have been moving steadily inward, from ordinary measurement to sharper probes, from sharper probes to quantum uncertainty, and from uncertainty to the uncomfortable realization that reality at very small scales does not sit still in the tidy way our instincts would prefer. That alone is enough to make the microscopic world feel a little unruly. But now the story becomes more serious, because the strange behaviour of the quantum world is only half of the difficulty. The other half comes from gravity, which for most of this journey has been standing quietly in the background, looking almost too mild to matter. And that is exactly what makes the next turn so deceptive. In everyday life, gravity feels obvious but simple. It keeps your feet on the ground, your coffee in the cup, your books on the shelf, and your best intentions about exercise firmly attached to the sofa. It pulls apples downward, planets into orbit, and people toward the centre of the Earth whether or not they have had enough sleep to appreciate the experience. Because gravity is so familiar, it is easy to imagine that we already understand it in a complete and comfortable way. But the physics of gravity is not simple at all. It only seems simple because we usually encounter it under gentle conditions. Modern physics describes gravity through general relativity, and that description is one of the great achievements in human thought. Gravity, in this view, is not merely a force reaching out invisibly across space in the old Newtonian sense. It is the curvature of space-time itself. Matter and energy tell space-time how to curve, and curved spacetime tells matter how to move. That sentence has become famous because it captures something extraordinary with misleading neatness. It sounds almost conversational, as though the universe is engaged in a civil exchange of letters. In practice, it means that space and time are not fixed containers. They are part of the drama. They bend, stretch, and respond. Quantum mechanics, by contrast, governs the microscopic world. It tells us how particles behave, how energy comes in discrete amounts, how probabilities replace classical certainty, and how the act of measurement is tied to the structure of the system being measured. Quantum theory is astonishingly successful. It predicts experimental results with a level of accuracy that sometimes borders on the absurdly good. It explains atoms, chemistry, electronics, radiation, and much of the modern world besides. If you're using a phone, a computer, a laser, or a medical scanner, you're benefiting from quantum theory whether or not you feel like writing it a thank you note. So far, so triumphant. We have two brilliant theories. One handles the very small, one handles gravity and the large-scale structure of space-time. Each works magnificently in its own domain. One might be tempted to assume that the universe is therefore thoroughly accounted for, save perhaps a few details that can be sorted out by some future generation, armed with cleaner data and stronger coffee. Unfortunately, the two theories do not fit together in the way that such optimism would prefer. This is not because one of them is obviously wrong. That would almost be a relief. Science is good at discarding old theories when new evidence forces the issue. But here the situation is more awkward. Both theories are right, in the sense that both are spectacularly successful wherever we can test them. The trouble appears when we reach situations where both should matter at the same time. Then the seams begin to show. For most of physics, the separation is manageable. In an atom, quantum effects matter enormously, but gravity is so weak compared with the other interactions that it can be ignored without regret. In the motion of planets, stars, and galaxies, gravity matters enormously, while quantum effects are usually negligible at the scale of the whole system. The two theories live side by side because nature often gives them separate jobs. One handles the tiny, the other handles the massive, but not always. There are places in the universe where the tiny and the massive stop minding their own business and start interfering with each other. The very early universe is one such place. If you go back far enough toward the beginning, everything was compressed into conditions of immense density and energy. The universe was not only small in extent, it was intense beyond ordinary description. Under such conditions, quantum effects cannot be ignored, and neither can gravity. The whole cosmos becomes both microscopic in a sense and gravitationally extreme. That means we need a theory that includes both quantum mechanics and gravity at once. At present, we do not have a complete one. Black holes present another version of the same problem. Far from a black hole, general relativity describes gravity beautifully. Near the event horizon, relativity still does impressive work, but deep in the heart of the classical description lies the singularity, a place where curvature grows without bound, and the equations cease to provide a sensible physical picture. Whenever a theory predicts that physical quantities become infinite in this way, physicists do not throw a party. They take it as a warning sign that the theory is being pushed beyond the range where it can be trusted on its own. And since black holes are also objects whose behaviour must somehow be consistent with quantum principles, the tension only grows sharper. Then there is the Planck scale, the realm we are moving toward in this script, where distances are so small and energy so high that quantum uncertainty and gravitational effect should become equally important. That is the collision point. Not a literal crash, of course, with space-time and particles meeting in a cosmic traffic dispute, but a conceptual collision. The assumptions built into quantum mechanics and the assumptions built into general relativity no longer sit comfortably together. It helps to see exactly why. Quantum mechanics is usually formulated on a fixed background. Even when the theory deals with fluctuating fields and uncertain outcomes, it tends to assume a stable stage on which those events play out. There is a space-time arena, and the quantum objects evolve within it. The stage is there first, and the actors perform on it. General relativity refuses that arrangement. In relativity, space-time is not a fixed stage. It is dynamical. It responds to matter and energy. It curves, changes, and becomes part of the physical content of the world. The stage is not separate from the actors. It is tangled up with them. This difference is not just a technical quibble. It goes straight to the heart of what the theories think reality is made of. Quantum mechanics says the basic constituents behave probabilistically and can exist in superpositions of possibilities until measurement produces outcomes. General relativity says space-time geometry is smooth and classical, at least in the standard theory, and determines how objects move. So one theory wants the contents of the universe to be quantum and fluctuating. The other treats the geometry of the universe as smooth and definite. When the contents become energetic enough to affect geometry at the smallest scales, those attitudes can no longer be kept apart. Imagine trying to choreograph a dance in a room where the dancers are allowed to blur, overlap, and exist in combinations of motions, while the floor beneath them is supposed to remain perfectly smooth and fixed. Then imagine realizing that the dancers are energetic enough to make the floor bend and ripple under their steps. You can no longer describe the dance by keeping the floor classical and the dancers quantum. The floor itself has joined the performance. That is roughly the problem of quantum gravity. One natural response is to say, fine, then let us quantize gravity as well. If the electromagnetic field can be quantized, perhaps the gravitational field can too. This is a reasonable thought, and physicists have pursued it in several forms for many decades. In simple terms, the hope is that gravity might also have quantum carriers, often imagined in theory as gravitons, just as light is associated with photons. But when one tries to build a full quantum theory of gravity using the methods that work for other forces, severe mathematical trouble appears. The calculations generate infinities that cannot be controlled in the usual way. The theory becomes non-renormalizable, which is a forbidding technical term for a very impolite refusal to behave. Now, infinities in physics are sometimes signs that one has taken an approximation too far, or asked a question the wrong way. They are not always fatal. But persistent, uncontrollable infinities are serious warnings. They suggest that the straightforward route to quantizing gravity is incomplete or misguided. And so physicists have spent decades exploring alternatives. String theory, loop quantum gravity, causal sets, emergent space-time ideas, holographic principles, and several other approaches all try in one way or another to resolve this conflict. Each has deep insights. None has yet delivered a universally accepted final answer backed by decisive experimental confirmation. There is something almost comic in the situation, though physicists tend not to laugh when it keeps them up at night. The two best theories we have are each masterpieces. Put them together carelessly, and they begin behaving like two genius architects who designed marvelous wings of a building, but forgot to agree on what should happen where the corridors meet. That meeting point matters because measurement depends on it. If space-time at very small scales is not smooth and classical, then the whole notion of a sharply defined distance becomes questionable. You cannot casually measure the position of a particle relative to a background that is itself undergoing quantum fluctuations. The ruler would be fluctuating with the thing it is trying to measure. The grid would not sit still. The clock would not tick against a calm geometric backdrop. Everything that makes ordinary measurement meaningful would be drawn into the same zone of uncertainty. This is what people mean when they say quantum mechanics collides with gravity. They do not simply mean that both effects are present at once. They mean that the conceptual foundations of the two theories clash in such a way that our usual physical language begins to strain. Quantum mechanics says uncertainty is fundamental. General relativity says geometry is dynamical. Put those together and you are led toward the possibility that geometry itself becomes uncertain. Space may no longer be a smooth stage that can be divided indefinitely. Time may no longer flow against a fixed backdrop. The very arena of physics becomes part of the quantum problem. That is a much deeper crisis than merely lacking a more powerful detector. It is not just that the answer is hard to obtain. It is that the thing we are trying to ask about may no longer be describable in the old terms. There is a related issue that makes this collision even more striking. Quantum theory is deeply connected to probability amplitudes, interference, and the idea that different possible histories can contribute to a physical process. General relativity, by contrast, is built around definite spacetime geometry. Once geometry itself becomes subject to quantum uncertainty, one has to ask what it even means for spacetime to have many possible configurations contributing at once. Does the universe briefly entertain multiple geometries? Does causality remain clean? What becomes of near and far if the metric structure itself fluctuates? These are not decorative questions. They are unavoidable once gravity joins the quantum party. And that party, one must admit, is not especially well supervised. This is why the Planck scale occupies such an important place in theoretical physics. It is the scale where the collision cannot be ignored. Above it, one may continue using quantum field theory on an effectively fixed background for many purposes, or general relativity with only tiny quantum corrections for others. Below or near it, the compromise breaks down. One cannot pretend the stage is classical while the actors are quantum, because the actors carry enough energy to warp the stage itself. Nor can one keep the stage smooth while probing it with quantum precision, because the act of probing becomes entangled with gravitational back reaction. You can see the logic building now. To localize something more and more precisely, you need probes of shorter and shorter effective wavelength, which means greater and greater energy. But energy gravitates. It curves space-time. So the very energy required to sharpen the measurement begins to alter the geometry of the region you're investigating. The more precisely you try to define a location, the more seriously gravity objects. At extreme enough concentration, the measurement process itself threatens to create a region from which information cannot escape in the ordinary way. That possibility is one of the reasons physicists suspect that the Planck scale marks a genuine limit to operational measurement. There is a certain elegance in this, though it is the sort of elegance that comes with a headache. Quantum mechanics tells you that sharper localization comes with uncertainty and disturbance. General relativity tells you that concentrated energy alters space-time. Put the two together, and nature appears to enforce a kind of limit. It is not merely that we have not yet found a way to look smaller. It may be that looking smaller in the ordinary sense destroys the calm conditions required for the notion of smaller to remain meaningful. This collision also changes how we think about emptiness. In ordinary language, empty space sounds like nothing much at all. A blank stage, a gap between objects. Quantum theory already complicates that by telling us the vacuum is not truly empty. Fields fluctuate. Virtual processes contribute. The vacuum has structure. General relativity complicates matters further by saying that space-time itself carries geometry and responds to energy. When these two ideas are brought together, empty space begins to look less like a passive absence and more like an active participant. At the smaller scales, it may be restless, fluctuating, and structurally unstable in ways that our classical picture cannot capture. That possibility has led physicists to phrases like space-time foam, a suggestive term meant to capture the idea that at unimaginably small scales the smoothness of space-time may break down into something frothy and fluctuating. Whether that picture is literally correct is another matter. Physics does not hand out poetic metaphors without later checking the bill, but the image is useful because it emphasizes the central point. The calm geometric background of classical relativity may be only an approximation, just as the smooth surface of the sea looks calm from a great height while hiding a great deal of local motion. Once you accept that, the Planck scale stops looking like just a number and starts looking like the place where the old peace treaty between the two great theories expires. Up to a point, quantum mechanics and gravity can ignore one another. Beyond that point, they must negotiate directly, and the negotiations are not yet complete. This is also why physicists care so much about finding a deeper theory. They are not searching for novelty merely for its own sake. They are trying to repair a genuine fracture in our understanding. A complete theory of quantum gravity would not simply add another decorative layer to physics. It would tell us what spacetime really is at the smallest scales. It would explain whether geometry is fundamental or emergent. It would clarify whether the Planck length is a real lower bound, a sign of discrete structure, or the shadow of something even stranger. It would help us understand black holes, the earliest universe, and the operational limits of measurement itself. For now, though, we live with a fascinating incompleteness. We know enough to see where the conflict arises. We know enough to trust that it matters. We know enough to suspect that below a certain scale, our usual ideas of distance and localization fail because quantum uncertainty and gravitational response become inseparable. But we do not yet have the final framework that says exactly what replaces them. And perhaps that is the right place to pause for the moment, because once quantum mechanics and gravity collide, the next question becomes unavoidable. If the smooth geometry of space-time may not survive intact at the smallest scales, then what exactly is the Planck length supposed to represent? Is it a final pixel, a fundamental grain, a hard lower limit, or something subtler than all of those familiar pictures? That is where the discussion naturally moves next, toward the strange possibility that the Planck length is not merely very small, but a sign that nature may refuse to let space be divided forever in the way our intuition once assumed. So now we come to one of the most tempting images in all of modern physics. If there is a limit below which distance can no longer be meaningfully measured in the usual way, is the Planck length nature's final pixel? Is space, in some profound hidden sense, made of tiny indivisible units, the way a digital image is made of dots on a screen? Have we reached the point where the old dream of endless divisibility gives way to a universe built from the smallest possible bits? It is an attractive idea, perhaps too attractive. Human beings are very fond of pictures that make difficult things feel manageable. We like to turn puzzles into objects and mysteries into machinery. If the world below the Planck scale refuses to behave in the ordinary way, then surely we think it must simply be made of little blocks, little tiles, little cubes, little grains of distance, all laid down by the cosmos with the sort of neatness that would satisfy both a geometer and a very tidy floor installer. There is something comforting in that image. It makes the universe feel understandable in a familiar way. Instead of asking what it means for space-time itself to become uncertain or emergent or dynamically unstable, we get to imagine something almost domestic. Space is just pixelated. A cosmic screen. Zoom in far enough and eventually you stop seeing smooth lines and start seeing the tiny units from which the picture is built. Problem solved. Tea all around. Except the problem is not solved at all. Because while the final pixel metaphor is useful as a first approach, physics has not actually proved that spacetime is made of little square chunks in any literal sense. The Planck length is not a discovered brick lying at the bottom of reality, with a label on it saying smallest piece. It is something subtler and more demanding. It is a scale at which our current theories strongly suggest that the ordinary notion of distance stops being secure. That is not quite the same as saying that distance is built from hard little units in the way a computer image is built from pixels. The difference matters, and it matters a great deal. A pixel on a screen is part of an engineered system. It has a fixed size. It occupies a place in a grid. It is one element among many similar elements, and the whole image arises because those elements are arranged in a regular pattern. If space-time were literally pixelated in exactly that way, then we would be saying something very strong about the structure of reality. We would be saying that space comes with a built-in lattice, an underlying arrangement of minimal cells. we would be claiming not just that measurement fails below a certain scale, but that there is a definite smallest unit from which larger distances are assembled. Some approaches to quantum gravity do hint at forms of discreteness, and so the final pixel image is not nonsense, but it is not established fact either, and even where theories propose something discrete, what they mean is often much stranger than the simple screen analogy suggests. The fundamental structure may not be a rigid grid at all. It may be relational, algebraic, network-like, or emergent from something deeper that does not resemble little blocks of space in the ordinary sense. This is one of those places where language tries its best and still looks a little underdressed for the occasion. We say pixel because we want a handle, a point of contact with ordinary life. But the Planck length is not a tiny glowing square hiding behind matter. It is a warning light on the dashboard of physics. It tells us that the assumptions built into smooth geometry and arbitrarily fine measurement can no longer be trusted without question. To see why this distinction matters, it helps to think about what smoothness really means in physics. In ordinary geometry, a line can be divided forever. Take a segment and split it in half, then split the half in half, then again. There is no obvious end to that process in pure mathematics. Continuity allows endless subdivision. You can always imagine a smaller interval. Classical physics inherited much of that confidence. Space was treated as a continuous background. Points could be specified exactly in principle. Distances could be made arbitrarily small in theory, even if practical measurement was never perfect. The Planck length changes the tone of that assumption. It says that if you try to localize a region of space more and more sharply, the very means of localization begin to undermine the framework in which localization makes sense. Quantum uncertainty grows important. The required energy grows extreme. Gravity responds to that energy. This space-time you hope to inspect as a calm background becomes part of the disturbance. In that situation, the idea of asking for a shorter and shorter distance may lose operational meaning, not because mathematics prohibits smaller intervals, but because nature may not permit an experiment that distinguishes them while preserving the concepts being used. This is why some physicists talk about the Planck length as a minimal, meaningful length, rather than simply the smallest length in a naive mechanical sense. It marks a limit on what length can mean in physical practice, given the laws we know. That is a deeper and more careful statement than saying the universe is definitely built from tiny cubes. Still, the cube image persists because it captures something we instinctively grasp. We know from experience that smooth appearances can emerge from underlying discreteness. A painting looks continuous from across the room, but up close it reveals brush strokes. A digital photograph looks smooth until magnification exposes the individual pixels. A fabric seems like one surface until you inspect the threads. So it is natural to wonder whether space-time itself behaves similarly. Perhaps the smooth space of our daily experience is only an approximation, a large-scale effect arising from more primitive ingredients. That possibility is taken very seriously in modern theoretical physics. The key caution is simply that we do not yet know exactly what those ingredients are, or even whether they should be thought of as spatial ingredients at all. It may be that space is emergent rather than fundamental. That is one of the most radical and exciting ideas in the field. Instead of imagining tiny bits of space assembling into larger space the way bricks assemble into a wall, some theories suggest that space may arise from patterns of relation, information, entanglement, or quantum structure that are not themselves straightforwardly spatial. If that sounds like the kind of sentence that causes a person to stare thoughtfully at the ceiling for several minutes, that is because it should. It is a genuine shift in the way reality may have to be described. We are so used to treating space as the obvious stage on which everything happens that it is difficult to imagine the stage itself as something secondary. Yet physics has already forced us into similar revisions before. Time once seemed absolute until relativity changed that. Matter once seemed solid and indivisible until atomic and quantum theory changed that. It would not be the first time science discovered that what looked fundamental was in fact emergent. This makes the final pixel question much more interesting. The most useful answer may be neither a simple yes nor a simple no. The Planck length may function like a limit to meaningful spatial resolution without implying that the world is made of tiny literal pixels in the way our computers are. Or perhaps there is some kind of discreteness, but it is not the regular, tidy discreteness our intuition reaches for. Nature may be chunkier than classical continuity suggests, but not in the familiar blocky style of a low-resolution screen. There is also a deep reason why a literal spatial grid creates difficulties. A fixed grid would seem to pick out preferred directions or preferred frames, and modern physics is generally very wary of that. Relativity teaches us that the laws of physics should not secretly depend on some hidden, universal rest frame or cosmic graph paper. If space were built from rigid little boxes laid down in one special arrangement, then preserving the symmetries that relativity holds dear would become quite tricky. That does not make discreteness impossible, but it means any acceptable version of it has to be subtle enough not to wreck the elegant structure already confirmed by experiment. So once again, the neatest first picture is likely too simple. The universe may not be a giant spreadsheet. Another reason the pixel metaphor can mislead is that a pixel is something directly viewable from above, as it were. You can inspect the screen, identify the dot, and point to it. But if the Planck length marks the scale where ordinary measurement breaks down, then whatever lies there is not available to us in that same straightforward way. We are not standing outside Spacetime with a magnifying glass large enough to peer down at its smallest tiles. We are creatures inside the system, using physical probes governed by the same laws as the thing being probed. That means the very act of trying to inspect the supposed pixel structure is constrained by the operational limits the Planck scale embodies. This is why the Planck length is often better understood as a threshold concept than as a literal object. It tells us where current descriptions lose their smooth confidence. It indicates the scale at which our usual notions of geometry, locality, and distance must be revised. It does not hand us a neat mechanical toy model and say, there you are, that is the final secret. And perhaps there is something healthy in that restraint. Physics is at its best when it distinguishes between a useful metaphor and a demonstrated structure. The pixel metaphor is useful because it helps us stop assuming infinite smoothness without limit. But physics has to keep asking what exactly is discrete, in what sense, according to which theory, and with what observational consequences. Those are harder questions, less tidy, and considerably less suited to decorative posters, but they are the right ones. Some approaches to quantum gravity imagine areas and volumes coming in discrete units, rather than space itself being laid out as a simple grid. Some describe fundamental strings rather than point particles, which changes what it means to probe arbitrarily small distances. Some suggest that space-time geometry arises from entanglement patterns in an underlying quantum description. Others propose causal structures more fundamental than smooth geometry. In each case, the Planck length plays a significant role, but not always as a little ruler mark on the edge of reality. More often, it appears as the scale where familiar space-time concepts are expected to give way to something deeper. That is a rather different kind of smallest. Not smallest like a pebble at the bottom of a pond, smallest like the point beyond which the old map no longer represents the terrain. There is also an important philosophical shift here. In ordinary thinking, if there is a smallest size, we imagine it as an object, the smallest bead, the smallest box, the final grain. But in modern physics, the deepest limits are often not object-like at all. They are limits on description, limits on measurability, limits on the simultaneous applicability of concepts that worked beautifully at larger scales. The Planck length may be one of those. It may not be the tiniest thing in the world so much as the place where our inherited idea of thing-size length stops functioning without modification, and yet the desire for a final pixel is understandable. It gives the mind something to settle on. It suggests closure. It says the reason you cannot go smaller is simply that there is nothing smaller to go to. But the universe may not owe us such a clean ending. It may instead offer a more subtle answer. You cannot go smaller in the ordinary measurable sense because ordinary measurable sense is built from assumptions that fail there. That is less satisfying to the instinct that wants a simple picture, but it may be closer to the truth. There is a quiet beauty in that possibility. It means the Planck length is not merely a barrier, it is a clue. It points not only to a limit, but to the existence of deeper structure beyond the limit of our current vocabulary. It says that the smooth space-time of everyday experience and classical relativity is probably an approximation, much as temperature is an approximation, describing the collective behavior of countless microscopic constituents. Temperature is real and useful, but it is not fundamental in the same way as the underlying molecular motion. Likewise, space-time may be real and useful at accessible scales while still emerging from something more basic. If so, then the Planck length is not just where the ruler stops, it is where a more profound description must begin. One might say this is where physics becomes almost archaeological, except that instead of digging downward through layers of soil, it digs downward through layers of concept. First the smooth world of ordinary objects, then atoms, then quantum fields, then the uneasy frontier where geometry itself may not be fundamental. At each level, the old familiar language survives for a while, then becomes approximate, then finally gives way. The Planck length seems to mark one of those handover points, and that brings us back to the central question. Is it nature S, final pixel? Perhaps in spirit, yes, if by that you mean a scale below, which ordinary smooth distance no longer retains its familiar meaning, but probably not in the naive literal sense of tiny squares laid out on a hidden screen. The metaphor is suggestive, not definitive. It helps the imagination take one step, but not the whole journey. By now, you can also see why the Planck length is inseparable from the problem of measurement. If this scale marks the boundary where the geometry of space stops being smoothly measurable, then trying to inspect anything below it is not like using a finer ruler on the same kind of surface. It is more like discovering that the surface itself no longer behaves like a surface in the ordinary sense. The background starts to shift under the concept. The language of shorter distance ceases to be innocent, and once that possibility is taken seriously, another implication follows close behind. If sharpening our view requires packing more and more energy into a smaller and smaller region, and if gravity responds to concentrated energy by warping space-time, then the act of looking closer may eventually become so extreme that the very region we are trying to examine collapses into something else entirely. At that point, the Planck length stops being merely suggestive and becomes part of a much more dramatic story about black holes, concentrated energy, and the astonishing price nature charges for asking to see too much too clearly. There is a point in this story where the whole business stops feeling like a quiet issue of better tools and starts feeling like a much more serious warning from nature. Up to now, we have been following a fairly natural line of thought. If you want to see something smaller, you use a sharper probe. If you want to pinpoint something more precisely, you use something with shorter wavelength and higher energy. If the world keeps yielding deeper layers of structure, then surely the main challenge is patience, engineering, and the occasional willingness to build very expensive machines in very large tunnels. That is a reasonable expectation, and it works well for a surprisingly long stretch of physics. But as we approach the Planck scale, a different problem appears. The problem is not simply that high-energy probes disturb the thing you're trying to measure. The problem is that energy itself has weight in the story. Not weight in the everyday sense of bathroom scales and awkward luggage at airports, but gravitational significance. Energy changes gravity. Energy curves space-time. And once you try to pack enough energy into a tiny enough region, the act of looking more closely begins to threaten the structure of the region you're trying to examine. This is where black holes enter the discussion, and they do not arrive as some dramatic side plot invented to spice up the script. They appear because general relativity takes energy seriously. If enough mass or energy is concentrated into a small region, gravity becomes so strong that not even light can escape. That is the basic idea behind a black hole. It is not a hole in the ordinary sense, like a missing patch in a road or a gap in a sock that has given up on respectability. It is a region where space-time is curved so severely that escape is no longer possible once you cross a certain boundary. That boundary is called the event horizon, and it matters here because it turns the whole logic of better probing on its head. Ordinarily, when you want more information, you send in more energetic probes and collect the return signal. But if the energy involved in the probing process becomes too concentrated, then instead of getting a cleaner signal back, you risk creating a situation in which the information is trapped behind a horizon. The region you are trying to inspect becomes hidden by the very gravitational effect produced by the energy you use to inspect it. There is something almost unfair about that, though from the point of view of the universe it is probably just consistent. You try to see a smaller region by using a more powerful probe. The more powerful probe brings more concentrated energy. The concentrated energy curves space-time more strongly. If you push that logic far enough, the process of trying to reveal the structure of the region causes that region to collapse behind a black hole-like boundary. You're no longer illuminating the target. You are burying it under the consequences of your own measurement. That is one of the deepest reasons people suspect there is a fundamental lower limit to operational measurement. Not because scientists become timid, not because future technology will run out of batteries, but because nature appears to charge an ever steeper price for asking sharper questions, and eventually the price may be so high that the question destroys the calm conditions required for an answer. To appreciate how remarkable this is, it helps to remember how different this is from the ordinary logic of science. Usually, more careful observation gives more information. Better clocks improve timing, better telescopes improve angular resolution, better microscopes reveal smaller structure. In each case, you can imagine progress as a steady refinement, but gravity introduces a non-linear penalty. More concentrated energy does not just improve your reach, it changes the stage on which the measurement takes place, and if the concentration becomes extreme enough, the stage itself folds into a form that blocks the very information you wanted. This is where the Planck scale stops feeling like a mysterious curiosity and starts feeling like the edge of a physical bargain. On one side, quantum theory says sharper localization needs more energetic probing and comes with greater uncertainty in other respects. On the other side, relativity says energy is never just along for the ride. It participates in shaping space-time. Put those together and you get a very unsettling conclusion. To localize a region more and more precisely, you must concentrate more and more energy there, but that very concentration eventually risks producing a black hole. At that point, looking closer is no longer a clean improvement. It becomes self-defeating. There is a useful analogy here, though, like all analogies, it should not be pushed too hard. Imagine trying to inspect the texture of a fragile sheet of ice by pressing harder and harder with a tool. At first, more pressure gives you better contact. You learn more. But beyond a certain point, the pressure stops helping because the ice cracks under the force. The closer inspection destroys the surface you are trying to inspect. Now replace the ice with space-time itself. Replace your tool with an ultra-high energy probe, and replace the crack with gravitational collapse. The comparison is crude, but the lesson is similar. There can be a threshold beyond which more aggressive measurement stops producing finer knowledge and starts producing a different physical situation altogether. That threshold is not arbitrary. It emerges from the way quantum mechanics and gravity jointly constrain what a meaningful measurement can be. If you try to mark off a region smaller than the Planck length, the energy required to resolve it may be enough to distort spacetime so severely that the region cannot function as an ordinary measurable location any longer. In effect, the universe says you may ask for a sharper spatial distinction, but the price of asking is to undermine the very notion of stable distance in that region. This is why black holes matter so much in this discussion. They are not merely exotic astronomical objects sitting in distant galaxies doing theatrical things for telescope headlines. They are part of the logic of fundamental measurement. They reveal that gravity is not passive. It does not sit politely in the corner while quantum theory does the interesting work. If you put enough energy in one place, gravity responds in the strongest possible way. It can seal off the region from the rest of space-time and deny you any simple access to what lies inside. There is also a subtle lesson here about information. In ordinary experiments, we assume that if we prod a system carefully enough, some information can come back to us. That is what a measurement is. We send in a probe and read the response. But a black hole complicates this picture drastically, because it is defined by the fact that certain information cannot escape in the ordinary way once the event horizon forms. So when probing energy becomes high enough to produce this kind of boundary, the measurement procedure is no longer merely invasive. It becomes informationally self-blocking. The thing you hope to learn is now hidden by the conditions created in the act of trying to learn it. That is an astonishing outcome if you stop and think about it. It means there is a link between knowing and not knowing that is enforced by gravity itself. Ask a coarse question, and nature may answer. Ask a sharper one, and nature may answer with more detail. Ask too sharp a question in too small a region, and nature may answer by creating a black hole and declining to provide further clarification. There is a certain dry humour in that. One imagines the universe not becoming angry exactly, but simply becoming uncooperative in an extremely precise way. This also helps explain why the phrase "just use more energy" becomes dangerous at the smallest scales. In many areas of particle physics, higher energies do reveal new structure. That strategy has been extraordinarily fruitful. Accelerators smash particles together at enormous speeds, and from the wreckage physicists infer what lies deeper. But the logic cannot continue forever without consequence. At some point, higher energy is not just a better probe, it is a stronger source of space-time curvature. And once that curvature becomes severe enough, the probing process changes category. The experimental arrangement no longer belongs to the same calm regime. This is not just a speculative fear invented to make the subject sound dramatic before bedtime. It follows from taking both of our great theories seriously at once. Quantum mechanics says shorter distance scales demand higher momentum and more concentrated probing. General relativity says concentrated energy curves space-time. The joint message is hard to avoid. There should be a scale where the demand for sharper resolution and the gravitational response to the required energy become inseparable. That is one of the reasons the Planck scale is treated as such a profound boundary. Another important point is that black holes are not only obstacles, they are clues. They tell us that any complete theory of the smallest scales cannot simply ignore gravitation until the end, and then bolt it on like an optional extra. Gravity is already built into the cost of asking the question. The appearance of black hole formation in these arguments suggests that space-time geometry and information are deeply linked at the Planck scale. The boundary between what can be measured and what becomes hidden may be telling us something fundamental about how reality organizes itself. This has led physicists into some of the most fascinating territory in modern theory. Questions about black hole entropy, information loss, holography, and the quantum structure of horizons all grow out of the realization that black holes are not just heavy objects. They are laboratories for the conflict between quantum theory, gravity, and information. Once you accept that trying to inspect extremely small regions may produce black hole-like behavior, you are forced to take seriously the idea that information about volume, area, and fundamental degrees of freedom may be arranged in ways unlike the naive pictures we inherited from classical geometry. Even without going that far, though, the basic message is already striking enough. The closer you try to look, the more energy you need. The more energy you pack into a tiny region, the stronger the gravitational response. Push too far, and the region ceases to be an ordinary target of measurement and becomes a trapped region instead. This means there is a profound sense in which gravity protects the Planck scale from direct inspection. It is not a fence, it is a consequence. And that word consequence matters. People sometimes speak as if the universe set up a mysterious rule saying no looking below this point. That makes it sound arbitrary, almost bureaucratic, as if nature has posted a sign and assigned a cosmic security guard. The real story is subtler and more satisfying. The limitation arises from the known behaviour of quantum systems and gravitating energy. It is not imposed from outside. It grows naturally from the physics we already trust in their respective domains. That is why so many physicists take the limit seriously. It is not merely a convenient slogan. It is the result of pushing our best ideas until they begin to constrain one another. There is also a broader philosophical lesson here about curiosity itself. We often imagine knowledge as the steady reduction of ignorance through more intense inquiry. Ask more carefully, measure more precisely, build a better machine. These are excellent instincts and science owes a great deal to them. But black holes remind us that curiosity is not exempt from the laws of the world it investigates. There may be questions for which increasing the intensity of inquiry changes the physical situation so much that the original question no longer has the form we expected. In other words, there can be a price for looking closer, not just in funding and engineering, but in principle. That does not make the quest hopeless. It changes the kind of answer we should seek. If direct localization below the Planck scale becomes self-defeating, then physics must look for indirect descriptions, deeper principles, and new frameworks in which the old spatial picture is not the starting point. Rather than imagining that a better magnifying glass will eventually sort things out, one begins to suspect that what is needed is a different concept of what space, energy, and information are at the most fundamental level. This is one of the reasons black holes have become so central in theoretical physics. They sit at the crossroads of so many deep problems. They involve gravity at its most severe. They challenge our understanding of time and causality. They raise hard questions about quantum information. And in the present context, they expose a limit to the simple idea that higher energy always buys better resolution. Sometimes higher energy buys a horizon instead. That is a wonderfully inconvenient fact. It means the route inward is not open-ended in the old way. You cannot simply keep turning the dial forever and expect nature to hand you ever smaller pieces of the same kind of answer. At some point the answer changes type. The microscope becomes a collapse engine. The probe becomes part of the gravitational problem. The target disappears behind a horizon generated by the act of targeting it. And once that is on the table, a new picture starts to come into view. If the smooth geometry of space-time cannot survive arbitrary localization, and if black hole formation lurks behind attempts to define too tiny a region too sharply, then perhaps space at the smallest scales is not smooth at all. Perhaps it fluctuates. Perhaps the neat concept of distance frays into something irregular, restless, and structurally unstable. This is where theorists begin reaching for images like space-time foam, not because they are trying to be poetic for the sake of it, but because they need some way to talk about a regime in which geometry itself may become turbulent, and that is the territory we are moving into next. If black holes teach us that looking too closely can destabilize the very region we are trying to inspect, then the next idea follows almost naturally. Perhaps the trouble is not only that measurement becomes too energetic. Perhaps at the smallest scales, space-time itself is no longer the calm, smooth background we have been picturing all along. Perhaps the problem is not simply that our ruler becomes inadequate, but that the thing we are trying to use the ruler on no longer behaves like a smooth surface in the first place. This is where physicists began using a phrase that sounds slightly whimsical and slightly alarming at the same time. Space-time foam. It is one of those scientific expressions that manages to sound almost friendly until you stop to think about what it implies. Foam is not a word people usually associate with the firm structure of reality. Foam belongs to bathwater, sea spray, shaving cream, and occasionally a badly poured pint. It suggests bubbles, froth, instability, and surfaces that only look solid from a distance. It is not what you would instinctively choose if you wanted to reassure people that space and time are dependable, and yet the phrase is useful because it captures an unsettling possibility. At everyday scales, space-time appears smooth. Distances can be marked out, clocks can be synchronized, geometry behaves with splendid reliability. Roads remain where roads are supposed to be. Chairs do not flicker between one side of the room and the other. A meter remains a meter. The entire business of ordinary life depends on space-time being stable enough that people can miss trains for human reasons, rather than because the platform fluctuated away beneath them. But physics is full of situations where smooth large-scale appearances hide restless small-scale structure. A table looks solid until atomic theory tells you it is mostly empty space, held together by forces and quantum rules. Water looks continuous until you remember it is made of molecules. A coastline seen from high above appears neat enough, but closer inspection reveals ragged detail, and closer still reveals something else again. The lesson appears again and again. What looks smooth from one scale may be highly structured from another. Space-time foam is an attempt to imagine that lesson applied to space and time themselves. The idea is not that the universe turns into literal soap bubbles at small scales, which would make interior design rather difficult. The idea is that if quantum mechanics applies to everything physical, and if space-time is itself part of the physical world rather than a passive backdrop, then perhaps space-time cannot remain perfectly smooth and definite at arbitrarily tiny scales. Instead, it may fluctuate. Its geometry may become uncertain, restless, and irregular. Distance may stop being a clean, stable quantity. Time may stop flowing against a perfectly calm geometric scaffold. The stage itself may acquire quantum jitters. That phrase quantum jitters may sound casual, but it points to something serious. In ordinary quantum theory, fields fluctuate even in what we call empty space. The vacuum is not a simple nothing. It has structure, energy, and restless behavior built into it. Particles and fields do not sit in perfect classical stillness. If space-time itself must eventually be treated quantum mechanically, then one expects a similar story there too. The geometry may not sit quietly at the smallest scales. It may fluctuate in ways that make exact distances and durations fundamentally fuzzy. This is not the same as saying that large objects visibly wobble, or that your living room is secretly an erupting quantum ocean. The effects, if this picture is right, would be tiny beyond imagination at accessible scales. Just as the graininess of a photograph is invisible from far enough away, the irregularity of space-time at the smallest scales would average out into the smooth geometry we know from ordinary experience and general relativity. The foam, if that is what it is, would only matter when we ask questions at scales so extreme that the underlying irregularity can no longer be ignored, and that is precisely what happens as we approach the Planck scale. Our ordinary notion of distance assumes that between two locations there exists a meaningful interval that can in principle be made more and more precise. Even if we cannot measure it perfectly in practice, we imagine that nature itself contains a definite value there to be approached ever more closely. Space-time foam challenges that idea. It suggests that below a certain level, the very notion of a sharply defined interval may fail, because the geometry we are trying to measure is not fixed. It fluctuates. The shortest distances do not sit still long enough to behave like the smooth intervals drawn in classical geometry. To see why this matters, think about what a distance measurement really needs. You need identifiable points or events. You need some stable geometry relating them. You need a signal or process that travels between them in a way that can be compared. You need a clock, a ruler, or some equivalent physical system that functions against a reasonably stable background. Now imagine that the background itself is fluctuating at the same scale as the distance you're trying to define. Suddenly every piece of the measurement becomes part of the problem. The endpoints are not sharply fixed. The path between them is not cleanly determined. The ruler is not resting on a stable floor. The clock is no longer ticking against a smooth temporal backdrop. The geometry itself has joined the uncertainty. That is what people mean by the breakdown of distance. Not that all size disappears in some mystical way, and not that meters and miles become meaningless in daily life, but that the deeper concept of arbitrarily fine spatial interval may no longer survive as we push toward the smaller scales. Distance works beautifully at ordinary scales. It remains useful and real in the regimes where our current physics has been tested. But below a certain point, it may stop being a fundamental building block and become instead an emergent approximation, good for the middle-sized world but not written into the deeper structure of reality. This is a difficult idea because distance feels so basic. You can doubt many things while still trusting the gap between one object and another. Space seems like the most obvious of all frameworks. Even time, for all its strangeness, often feels more suspect than distance. But modern physics has a habit of taking the most obvious background features and exposing their dependence on deeper structure. Once relativity showed that measurements of space and time depend on motion and gravity, the old fixed stage was already weakened. Spacetime foam pushes the revision further still. It says that at sufficiently small scales, even the geometry described by relativity may be only a large-scale average, much as temperature is an average description of microscopic motion. This is why foam is such a helpful, if imperfect, image. Foam has no single smooth surface when examined closely. It is full of local irregularities, pockets, bubbles, and shifting boundaries. Step back and you may speak meaningfully of a layer of foam, a thickness, a shape. Step closer and the neat surface disappears into restless local structure. The comparison is not exact, but it helps us picture a world in which spacetime is smooth only in the same way that a beach may look smooth from an airplane. The closer you get, the less the old description captures the details. Of course, physicists are careful here, because foam is still only a metaphor. Different theories of quantum gravity suggest different kinds of underlying behaviour. Some imply that areas and volumes come in discrete units. Some suggest networks of relations more basic than geometry. Some suggest that space-time emerges from quantum entanglement or information-theoretic structures. Some emphasize causal order rather than smooth spatial extension. What unites many of these ideas is not the literal image of bubbles, but the suspicion that classical space-time cannot remain exact all the way down. This has far-reaching consequences. If distance breaks down at very small scales, then many of the concepts we use casually in physics have to be re-examined. Near and far may cease to be fundamental. Locality, the idea that interactions happen at identifiable neighbouring points, may need revision. Even the notion of a path from one place to another becomes unstable if place itself is not sharply defined at the deepest level. We are accustomed to asking what is happening here and how far is it to there, but those questions assume a geometric framework with much more solidity than the foam picture allows. One reason this possibility is taken seriously is that the alternatives become increasingly difficult to maintain. If you insist that spacetime remains perfectly smooth and classical at arbitrarily small scales, then you run headlong into the problems we have already discussed. Quantum uncertainty refuses to stay quiet. The energy required for sharper and sharper localization grows more and more extreme. Gravity responds to that energy. Black hole formation threatens the probing process. All of this suggests that smooth distance cannot be a limitless concept in physical practice. Spacetime foam is one way of expressing what may replace that limitless smoothness. It also changes the way we think about emptiness. In everyday language, empty space sounds like a blank gap between things, a clean absence. But in modern physics, empty space is already not truly empty. Quantum fields fluctuate there. Energy conditions matter there. Virtual processes contribute there. Add gravity to the story, and the emptiness becomes even richer. If space-time geometry itself fluctuates, then even the vacuum carries a restless structural character. Empty space is not a passive box waiting to be filled. It is an active player in the game. This is one of those moments where physics becomes both more difficult and more concrete at the same time. Difficult because the old clear pictures no longer work. Concrete because the limits arise from very physical considerations. We are not speculating idly about dreamy abstractions. We are following the consequences of taking quantum uncertainty and gravity seriously together. If those principles are both true, then the smooth geometry we rely on so confidently in ordinary measurement probably cannot be fundamental at every scale. There is also a subtle but important shift in the meaning of measurement itself here. Earlier, measurement was already seen to be an interaction. Now it becomes something even more delicate. A measurement of distance assumes that the geometry being measured is not itself subject to violent fluctuation on the same scale. But if space-time foam is real in some form, then distance at the smallest scales is not a fixed property waiting to be read off. It is entangled with the fluctuating state of the geometry. The distinction between measuring an object and measuring the stage on which the object exists becomes harder to maintain. There may be no clean stage at all. This helps explain why some physicists think space and time are emergent rather than fundamental. If distance becomes fuzzy and unstable at the Planck scale, perhaps it is not because the deepest level contains badly behaved little bits of classical space, but because there is no classical space down there to begin with. Perhaps what we call space emerges only when many more basic ingredients are arranged collectively, the way a fluid emerges from molecules or a traffic jam emerges from cars. At the level of individual drivers, there is no object called a traffic jam floating above the road. The jam is a higher level pattern. Likewise, space-time may be a higher level pattern arising from deeper quantum structure. That possibility would explain a great deal. It would explain why geometry works so well on large scales and yet seems to become troublesome at the smallest ones. It would explain why the Planck scale appears as a threshold of meaning rather than merely as another small number, and it would explain why our attempts to apply ordinary distance concepts below that scale keep running into paradox, uncertainty, and gravitational collapse. We may be trying to use a large-scale concept outside the regime where it is fundamental. Still, one has to be honest about what remains unknown. Space-time foam is a suggestive framework, not a completed doctrine. We do not yet have a final experimentally verified theory that tells us exactly what the geometry of reality looks like at the Planck scale. That is why theoretical physics remains so active here. It is not because physicists enjoy making life difficult for one another, though there are occasional signs of that too. It is because the evidence from our best existing theories strongly points toward a breakdown of the old picture, while the new picture is still being assembled. This is also why the breakdown of distance should not be mistaken for a breakdown of science. It is the opposite. Science advances by learning where its old concepts stop being adequate. Once, absolute time seemed unquestionable. Then relativity showed where that concept fails. Once, deterministic classical trajectories seemed like the default language of reality. Then quantum mechanics showed where that language fails. Now, smooth space-time and endlessly divisible distance may be approaching the same kind of boundary. That is not a sign of collapse. It is a sign that we are reaching the edge of one successful approximation and beginning to glimpse the outlines of a deeper one. There is something reassuring in that, even if the subject itself is unsettling. The universe is not becoming irrational. It is remaining consistent while our inherited categories struggle to keep up. Foam is not chaos for the sake of chaos. It is a reminder that smoothness may be a large-scale luxury. The world can be lawful without being simple in the way our middle-sized brains would prefer. So when we speak of space-time foam, we are really speaking about the suspicion that the deeper structure of reality does not support an endlessly smooth geometry. We are speaking about the possibility that below a certain scale distance ceases to be a clean, fundamental notion, because the geometry itself is fluctuating, relational, or emergent. We are speaking about the collapse of an old certainty, namely that space can always be subdivided further while remaining the same kind of thing. And once that certainty goes, the question that has been following us from the beginning returns in a sharper form. If space-time itself becomes unstable, and the very idea of distance breaks down, then why exactly does physics lose its ruler there? And what does it mean to say that below the Planck scale, the ordinary tools of measurement no longer have anything definite left to grip? By now, the shape of the problem is beginning to show itself with unusual clarity. At first, the Planck scale may have sounded like just another tiny frontier, another place where science had not yet managed to build a sufficiently heroic machine. But after everything we have followed so far, the real issue looks different. Physics does not run out of ruler below the Planck scale because human beings are clumsy with instruments, or because laboratories have somehow failed to order enough polished mirrors and particle detectors. It runs out of ruler because the very idea of a ruler depends on assumptions about space, time, matter, and measurement that may no longer hold there. That is the heart of it. The ruler fails not because it is badly made, but because the world it was meant to measure stops behaving like the kind of world a ruler can describe. That may sound almost obvious after all the ground we have covered, but it is worth lingering there, because this is the point where several strands of the story finally tie themselves together. A ruler is not just a stick with markings. In physics, a ruler is any stable system that lets you compare one interval with another. It assumes that distance is meaningful. It assumes that 2 points or events can be distinguished in a sufficiently definite way. It assumes that the geometry relating them is calm enough for those distinctions to matter. It assumes that the act of measuring the interval does not destroy the interval as a usable concept. Those are very generous assumptions, and for most of the world we inhabit, they work beautifully. They work so well that we stop noticing them. A room can be measured. A road can be measured. The distance from the Earth to the Moon can be measured. Even atoms and smaller structures can be assigned meaningful scales through clever indirect methods. Science has become remarkably good at extending the idea of the ruler far beyond everyday life. We have built clocks so precise they can detect tiny changes in gravity. We have built instruments that infer the structure of matter from collision data. We have learned to measure things no eye will ever directly see. That success is part of what makes the Planck scale so striking. It is not the first difficult thing science has faced. It is the place where difficulty begins to look less like a challenge of refinement and more like a challenge to the underlying framework itself. You can think of it this way. In ordinary measurement, error comes from noise, limited resolution, imperfect calibration, or insufficient control over the system. If the result is fuzzy, you improve the setup. You cool the apparatus, reduce vibration, increase sensitivity, or repeat the trial until the signal becomes clear. All of that belongs to the normal logic of experimental progress. But below the Planck scale, the problem is not merely that the signal is buried under noise. The problem is that obtaining the signal requires a probing process so extreme that the quantity you hope to define no longer sits inside a stable stage. This is why the earlier steps in the argument matter so much. To resolve smaller distances, you need shorter wavelength probes. Shorter wavelength means higher energy. Higher energy means greater disturbance. Quantum mechanics tells you that sharper localization comes with unavoidable trade-offs. General relativity tells you that concentrated energy changes space-time geometry. Push both ideas together far enough, and the cost of asking for finer spatial resolution becomes the destabilization of the very region whose spatial structure you were hoping to clarify. At that point, what exactly is the ruler measuring? That question is not rhetorical. It is the central difficulty. A ruler works only when there is something sufficiently stable and sufficiently well defined for the ruler to compare. If space-time at those scales fluctuates, if localization requires enough energy to curve the region significantly, if black hole formation becomes a possibility, if the endpoints of your interval are themselves caught up in quantum uncertainty, then the ruler has no clean target. The failure is not in the markings. The failure is in the physical meaning of the interval. This is one reason the Planck scale is best understood as a limit on operational meaning. Physics is not content with mathematical imagination alone. It asks what can, even in principle, be measured by some physically realizable process. Below the Planck scale, the process itself appears to run into contradiction. To define the interval more sharply, you need a more violent probe. The more violent probe reshapes the geometry. The reshaped geometry defeats the original attempt at clean localization. In trying to sharpen the ruler, you erase the line it was meant to read. There is something almost elegant about that, even if it is deeply inconvenient. Nature does not merely say no. It says that below a certain scale, the old form of the question stops making physical sense. That is a subtler answer than a wall or a lock. It is more like discovering that a certain kind of map only works on dry land, and that you have now sailed into waters where the coastline, the compass, and even the idea of fixed direction all begin to fail together. This also explains why it is misleading to imagine the Planck scale as just another hidden layer waiting to be photographed. The problem is not that the hidden layer is shy. The problem is that the procedure of photographing presumes a stable geometry, a controllable interaction, and a meaningful notion of smaller than. If all of those begin to unravel together, then looking deeper in the ordinary sense becomes the wrong idea. Physics runs out of ruler because it is still trying to use a concept built for smooth space-time on a regime where smooth space-time may no longer be fundamental. And this is where the metaphor of the ruler becomes especially useful. A ruler is a device of comparison. It does not create distance, it presumes it. It does not generate geometry, it rests on it. If the geometry itself becomes uncertain or emergent, then no ordinary ruler can get underneath that fact, because any ruler is already part of the geometric picture being questioned. You cannot use a classical measuring rod to settle whether classical distance remains meaningful at arbitrarily tiny scales any more than you can use a shadow puppet to settle the structural integrity of the stage. There is another aspect to this that often gets overlooked. Measurement in physics is never just about a single object. It is always about a relation between the object, the apparatus, and the background assumptions that make the result interpretable. A location is defined relative to something. A duration is defined by a clock process. An interval is defined through geometry and signal exchange. Once the background itself becomes physically unstable, the distinction between system and apparatus begins to blur. The measuring device is no longer outside the problem. It is entangled with it from the start. This is particularly severe at the Planck scale because there is no safe external vantage point. We are not outside space-time, inspecting it from a distance with tools made of some superior substance exempt from the laws in question. Every apparatus we can imagine is made of matter and energy. Every probe is physical. Every exchange of information is governed by the same quantum and gravitational principles as the target. So if those principles jointly imply a limit to meaningful localization, no clever arrangement of ordinary physical tools can simply step around the issue. That does not mean nothing exists below the Planck scale in some dramatic philosophical sense. Physics is not saying the universe falls off a ledge there like a badly designed stage set. The more careful statement is that our present concepts of distance, position and measurement cease to function reliably. Something may well underlie the space-time we know. In fact, many physicists strongly suspect that something does, but if it does, it may not be spatial in the ordinary way. It may not be made of smaller pieces of familiar distance. The ruler fails because the deeper level may not be the kind of thing a ruler can describe. That possibility is both frustrating and exciting. Frustrating because it denies us the comforting picture of simply zooming in forever. Exciting because it suggests that space-time itself may be emergent, a large-scale structure arising from deeper principles. If that is true, then asking for a distance below the Planck scale may be a bit like asking for the exact temperature of a single molecule. Temperature is real and measurable at the right level, but it is not the right concept at the level of one molecule. Likewise, distance may be real and measurable across a vast range of scales, yet still not be fundamental all the way down. This would mean that physics runs out of ruler for the same reason it once ran out of absolute time and perfectly definite classical trajectories. The old concept worked magnificently in its domain, then began to fail when pushed into a deeper regime. Science advances not only by measuring more, but by discovering when the very grammar of measurement must change. There is something important to protect here from misunderstanding. Saying that physics runs out of ruler is not the same as saying science gives up. Quite the opposite. It means science has become precise enough to identify the boundary where one conceptual toolkit stops being adequate. That is progress of a very serious kind. It is easy to celebrate new measurements and new particles and new images. It is harder, but perhaps more profound, to recognize that a limit has been reached where the next advance will not come from sharper versions of the same question, but from discovering a deeper language in which new questions can be asked. That is exactly what the Planck scale seems to demand. Not a better ruler, but a better understanding of what geometry is. Not a more polished lens, but a new account of what it means for anything to be local, distinct, or measurable in the first place. Not a louder insistence on old intuitions, but a willingness to let reality revise them. There is also a peculiar emotional lesson in this, if one is allowed a gentle human observation in the middle of all the physics. We often assume that knowledge means control, measure more accurately, and the world becomes more manageable. That is true often enough to be deeply persuasive, but the Planck scale suggests that there are regions where knowledge does not come from pressing harder with the same tools. Sometimes pressing harder changes the object of inquiry so drastically that the old style of control becomes meaningless. In that sense, the limit is not just about smallness, it is about humility. The universe may be willing to answer, but not always in the language we expected. And yet, even here, the story is not one of defeat. The failure of the ruler is itself a clue. It tells us that space-time is not likely to be the last word. It tells us that quantum theory and gravity are both touching a deeper truth neither can fully express on its own. It tells us that the Planck scale is not merely a tiny interval, but a signpost pointing beyond our present map. If distance becomes unstable there, that instability is not meaningless noise. It is evidence that geometry may emerge from something more primitive and more subtle. That is why so much of modern theoretical physics is aimed not at forcing one more decimal place out of a familiar measuring scheme, but at asking what could replace the scheme entirely. Perhaps the deep structure is a network of relations. Perhaps it is built from quantum information. Perhaps space-time emerges from entanglement. Perhaps geometry is secondary to something more basic, and the Planck scale marks the boundary where the secondary description breaks apart. Different approaches say different things, but they are united by the suspicion that below the Planck scale, the ruler is not merely too short, it is speaking the wrong language. Once you see that, the phrase physics runs out of ruler begins to sound less like an admission of failure and more like a diagnosis of transition. The old instrument, both literal and conceptual, has reached the edge of its jurisdiction. It worked across an astonishing expanse of reality, from tables and planets to atoms and particles and gravitational waves and cosmic expansion. But there comes a point where the assumptions packed into the notion of measurable distance can no longer be maintained all at once. Quantum uncertainty pulls in one direction. Gravitational back reaction pulls in another. The smooth background of classical geometry loosens underfoot. The ordinary ruler, however refined, has nowhere definite left to stand, and so the deepest reason physics runs out of ruler below the Planck scale is not that reality becomes irrational, it is that reality becomes more exacting than our inherited categories. The concepts of point, interval, and location that served us so faithfully through classical and much of modern physics may be emergent conveniences rather than ultimate ingredients. Below the Planck scale, we do not simply lose precision. We lose the right to assume that precision means the same thing it did above. That, I think, is the right place to leave the question for now, because once the ruler fails, a final and rather haunting issue comes into view. If measurement reaches a boundary where its own concepts begin to dissolve, then what lies beyond that boundary? not in the sense of a neat hidden chamber waiting to be opened, but in the sense of what science can still say when direct measurement no longer leads the way. At the edge of the measurable, we're left with one last frontier, not just the smallest scale, but the limit of knowing itself, and that is where the next stretch of the journey takes us. And so we arrive at the strangest point in the whole journey, not the smallest point, not the most energetic, not the most mathematically elusive, but the point where the question itself begins to turn and look back at us. Because once we ask why nothing below the Planck scale can be measured in the ordinary way, another question appears almost immediately behind it. What exactly do we mean when we say something lies beyond measurement? Are we saying it does not exist? Are we saying science must stop? Are we saying the universe has secrets and has decided, with the quiet firmness of an old librarian, that those particular shelves are not for public browsing? Or are we saying something subtler, something both more frustrating and more interesting, that the deepest layers of reality may still be there, but not in a form that our present ideas of measurement can cleanly reach? This is where the topic becomes especially delicate, because human beings have a habit of dividing everything into the visible and the invisible, the known and the unknown, the real and the imaginary, as if reality were a cupboard with neatly labelled drawers. Science has taught us again and again that things are rarely arranged so kindly. There are many ways for something to be inaccessible. Some things are hidden only temporarily, waiting for better instruments or better methods. Some are too distant, too faint, or too ancient to inspect directly, but leave clues from which we can infer them. Some can be described mathematically before they can be observed, and some appear to sit at the edge where the old language of observation itself becomes unstable. That last category is where we now find ourselves. It is tempting, when confronted with a limit like the Planck scale, to imagine a dramatic border, a final wall, a curtain dropped across the stage. Beyond this point the story ends. But physics rarely behaves like a storybook. Its boundaries are usually more unsettling than that. They are not neat fences so much as regions where familiar concepts become unreliable. The edge of knowing is not always a hard stop. Sometimes it is a zone of translation failure. We keep asking questions in the language that served us well at larger scales, and the universe keeps refusing to answer in that same language. That does not mean there is nothing there. It may mean that what is there is not built from the categories we were using. If space is emergent rather than fundamental, then asking what lies below the Planck scale in spatial terms may be like asking what lies north of the North Pole. The grammar of the question quietly assumes the very framework whose applicability is in doubt. Or to bring it down to a more domestic level, it may be like asking for the exact flavour of a cookbook. The cookbook is real. The recipes are real. The meals are real. But flavour belongs to the cooked food, not to the printed page. One can keep asking the question if one likes, but the category has drifted away from the thing it is trying to describe. This is one of the most important lessons science offers, though it is seldom the most comfortable. Reality does not always reward us for asking sharper versions of old questions. Sometimes progress comes from learning that the question itself must be rebuilt from the ground up. That has happened before. People once asked what force pushes the planets through perfect crystalline spheres. The better answer turned out to be that there were no such spheres. People once asked what medium light waves travelled through, as if light needed a cosmic version of air or water. The better answer turned out to be that this presumed background was not part of nature after all. In each case, the limit was not merely in the measurement. It was in the conceptual picture that had framed the inquiry. So when we stand at the edge of the measurable and ask what lies beyond, we should be careful not to smuggle in assumptions from the very framework that is now under pressure. Beyond measurement may not mean beyond reality. It may mean beyond this way of turning reality into stable distances, positions, durations, and signals. Beyond the ruler, beyond the clock, beyond the old smooth stage of space-time. And yet science does not simply give up when direct measurement falters, it changes tactics. That is one of its quiet strengths. Much of what we know already comes from things we never observe directly in any ordinary sense. No one has ever held a quark in their hand. No one has watched the early universe from a comfortable observation deck with a blanket and a notebook. No one has looked straight at curved space-time the way one looks at a tree. Instead, we infer, we model, we compare predictions with traces and patterns. We listen for indirect consequences. We ask not can we see it in the old simple sense, but what effects would follow if this picture were right. That is likely how the deepest progress beyond the Planck scale, if that phrase is even the right one, will have to proceed. Not by shining a brighter light into a smaller hole, but by finding principles whose large-scale consequences can be tested. A successful theory of quantum gravity may not begin by showing us a tiny picture of the fundamental structure of space-time, as if under an impossible microscope. It may begin by explaining black hole thermodynamics more deeply, by resolving puzzles in cosmology, by revealing new consistency conditions, by connecting geometry to information in ways we can test indirectly, or by predicting subtle signatures in the structure of the universe. In that sense, what lies beyond measurement is not necessarily sealed off from science. It may simply demand a more indirect form of contact, much like hearing someone in the next room not by seeing them directly but by noticing the floorboards creak and the teacups rattle. The evidence can still be real, the inference can still be rigorous, the knowledge can still be deep. It is only the mode of access that changes. There is also a more philosophical point here, though not in the vague decorative sense. The edge of knowing reminds us that science is not the same thing as total visual access. Science does not require that every meaningful thing be pictured as a little object sitting in a tiny place. That is one of the habits we inherit from daily life, and it is a useful one up to a point. But the most successful theories in modern physics are already telling us that reality is not always arranged in that familiar style. Fields, amplitudes, entanglement, geometry, information, symmetry. These are not always things that fit neatly into the mind as miniature furniture, and yet they are among the best ways we have found of describing the world. So perhaps what lies beyond measurement is not a hidden toy box of even smaller bits. Perhaps it is a deeper order that can be approached only through structural understanding rather than direct localization. Perhaps what is fundamental is not made of little places, but gives rise to place. Perhaps what is fundamental is not made of little times, but gives rise to duration. Perhaps at the deepest level, the universe is less like a tiny machine and more like a set of relations from which the familiar categories of here and there, before and after, emerge only in the appropriate limit. If that sounds abstract, it is because abstraction often increases when we approach what is more fundamental. This is not because physicists enjoy becoming difficult for sport, though one cannot rule out occasional enthusiasm in that direction. It is because the world itself seems to move away from the pictures built by ordinary perception. The closer we come to the foundations, the less reality resembles common sense, and the more it resembles a framework whose full meaning has to be learned rather than simply imagined. There is something humbling in that. Human beings are middle-scale creatures. We evolved to judge the distance to a branch, the speed of a moving animal, the firmness of the ground underfoot, the time between sunset and sleep. We did not evolve to intuit quantum geometry or the deep structure of black hole information. The fact that our instincts struggle near the Planck scale is not evidence of failure on the part of the universe. It is evidence that the universe was under no obligation to be built for the convenience of upright apes with opinions and coffee. And still, despite that, we have reached astonishingly far. We have inferred the expansion of the universe. We have uncovered the quantum structure of matter. We have detected gravitational waves from distant collisions of black holes. We have built clocks so precise they notice differences in gravity over tiny vertical separations. We have learned enough to know where our theories fit beautifully and where they begin to strain. That alone is a remarkable achievement. To know the limit of a concept is already to stand beyond innocence. This is why the edge of knowing is not merely a place of frustration. It is also a place of precision. It tells us where the next theory must do better. It tells us what any deeper framework must recover at large scales and revise at small ones. It tells us that space-time cannot remain both perfectly smooth and indefinitely measurable if quantum principles and gravity are both taken seriously. It tells us that measurement itself is not a neutral window, but a physical process with limits woven into the structure of the world. And perhaps most importantly, it tells us that the unknown is not all one kind. There is the unknown that waits to be measured, and there is the unknown that waits to teach us how measurement must change. The Planck scale belongs to the second kind. It is not simply a blank spot on the map. It is a place where the map is trying to tell us something about its own construction. There is a lovely irony in that. The more carefully science measures the world, the more clearly it discovers the conditions under which measuring ceases to be straightforward. Knowledge does not only expand outward, it also becomes more self-aware. It begins to understand its own tools, its own assumptions, its own domains of validity. A mature science is not one that claims to have a ruler for everything. It is one that knows which rulers work where, and why some of them fail when pushed too far. This makes the Planck scale feel less like a locked door, and more like a threshold of maturity in our understanding. We are no longer asking only what is there. We are asking what it would mean for anything to be there in a measurable sense. We are no longer asking only how small something can be. We are asking whether size itself remains a fundamental category. We are no longer asking only how to observe more deeply. We are asking what counts as observation when the background of observation becomes part of the quantum problem. That is a rather quiet revolution, but a real one. And there is another comfort hidden in it, especially for a topic that can sometimes feel austere. The edge of knowing is not the edge of wonder. In some ways, it is where wonder becomes most honest. It is easy to feel awe at a big starry sky or a dramatic black hole image, and rightly so. But there is a different, perhaps deeper kind of awe in realizing that the fabric of reality may be such that our best concepts are only local approximations, beautifully effective in their domain and yet not ultimate. There is something profoundly moving in the idea that the universe can be lawful and intelligible without ever being reduced to a set of easy pictures. So what lies beyond measurement? The truthful answer is that we do not yet know in any final way. That uncertainty should be stated plainly. There are candid theories, compelling ideas, elegant frameworks, and serious mathematical programs. There are hints that space-time may be emergent, hints that information and geometry are deeply linked, hints that locality may be approximate rather than absolute, hints that black holes are not just astrophysical objects but clues to the architecture of reality itself. But hints are not the same as completion. Science remains at work here, and honesty demands that we say so. Still, not knowing is not the same as knowing nothing. We know that the old picture fails. We know that sharper localization becomes self-defeating near the Planck scale. We know that quantum uncertainty and gravity jointly force a crisis in the ordinary idea of smooth, measurable distance. We know that any deeper theory will have to explain why space-time looks classical at large scales, while becoming problematic at the smallest ones. We know that the edge of measurement is real enough to guide theory, even if the terrain beyond it is not yet fully charted. And perhaps that is the gentlest way to end the journey. Not with a grand declaration that the deepest secret has been opened, nor with a dramatic insistence that it never can be, but with a quieter recognition. The universe allows us a remarkable amount of access, but not always in the form we first expect. It gives us clocks and rulers, then teaches us where clocks bend and rulers fail. It lets us speak of space and time, then shows us that those words may be approximations drawn from deeper structure. It answers many questions, and in answering them, it teaches us how to ask better ones. So if you find yourself lying there now, a little drowsy perhaps, and wondering what sits beyond the last measurable scale, it may help to think of it not as a dark blank region where science stops breathing, but as the place where our present language grows thin. Somewhere beneath the smoothness of the world we know, beyond the reach of ordinary measurement, there may be a deeper grammar from which space, time, matter, and even distance itself emerge. We do not yet speak it fluently, but we have learned enough to know that it is there, waiting not for a louder question, but for a wiser one. And in a way that has always been the real story of physics. Not the conquest of mystery, but the patient refinement of how we stand in relation to it. Not the elimination of wonder, but its clarification. Not the final end of questions, but the slow discovery of which questions the universe is prepared to answer, and which must first be asked differently. At the edge of knowing, that is more than enough to keep curiosity awake, even as the rest of us begin, very gently, to drift towards sleep.